Very good morning to everyone present here. அனைவருக்கும் காலை வணக்கம். May I now request everyone to get seated. First of all, I would like to let you know that this is not official inauguration for now. The official inauguration will start at 3 p.m. But for now, the morning time, what we are going to do is that we are going to have the pre-event showcase. As a part of this symposium, a team from IIT Madras had went all across the Bharat, all across the country, reached out to many colleges, did a lot of workshops on semiconductors, and we also did hackathon. We have given a problem statement to almost around 500 to 600 college students, and then we have got the we have got the finalist for now. So basically this session will be aiming at explaining how we did the workshop, how we did the roadshow, and how we did the hackathon. The problem statement will be discussed here, and then the solution also will be discussed here. May I now request, so basically the hackathon run in 4 categories. One is product track hackathon, the other one is that system software hackathon, Shakti FPGA solution hackathon, and we also had this core enhancement hackathon. So may I now request all the leads to present one by one on their experiences and then hackathon. Yeah, please. First, I would like to welcome the VSD to take over.
All right, so good morning, Chennai. Vanakkam, Chennai. Is it right? Okay, thank you. All right, I'll share my slides. Good morning, all of you. My name is Kunal Ghosh. I'm IIT Bombay Masters, and I have my own company, vlsssystemdesign.com. Today we are going to, so if you are over here, you are over here for just 2 days, and today and tomorrow. But the journey actually started like 45 days ago. I mean, we have been traveling across India. I'll show you some places. We have been traveling across India for close to 45 days, and now is the grand finale of the whole event. So a little bit of background. I'm going to take you through a little bit of a background. We started with something called as a roadshow. So there is something called as RISC-V roadshow. We go to colleges, we do the entire semiconductors, RISC-V and product development workshops over there. That's how the whole thing actually started. So the places that we went were, we started with IIT Gandhinagar. Anybody from IIT Gandhinagar? Anybody who has joined from IIT Gandhinagar? Or anybody from Gujarat? Is it too far from Chennai? Oh, okay, you have joined. You were there a part of the roadshow? Okay. So we have somebody from Gujarat also. Thanks for coming. I mean, we should clap hands for the guy from Gujarat who is coming all the way from a far away place from India. So Professor Joyce Macau was the one who actually organized the Gandhinagar event. Then we went to IIT Jammu. Dr. Siddharth, are you here? Dr. Siddharth from IIT Jammu. Okay, anybody from IIT Jammu has joined over here? IIT Jammu, anybody? Okay, it's really on the northern side of our country. But I have heard some professors from IIT Jammu have actually joined this particular event. They will be available for the next 2 days. From there, we went to IIT Bhubaneswar on Valentine Day. It was 14th Feb, and we were not celebrating Valentine, we celebrated RISC-V roadshow. A very typical RISC-V roadshow that we did at IIT Bhubaneswar. Anybody from Bhubaneswar? Orissa, Bhubaneswar, anybody who has came all the way from Bhubaneswar? Okay, fine. So some speakers will be joining in. I think today and tomorrow they might be joining in. And finally today we are at IIT Madras. So it's 2nd March, and we were there over here for the product thing, but now is the grand finale what we are going to do over here. Okay, so the hackathon, the product hackathon, it was a very exhaustive event for all the organizers. I mean, the way it was planned, it was completely transparent. Everybody knew what everybody was doing over here. So I'll explain a little bit about the process. 70 teams across all over India had participated. 70 teams had joined, and they were given close to 4 days of time for submission their product ideas. That is how it was done. Out of the 70 teams, 30 teams, they got based on their ideas. They got selected for the next level, and that level went on for 14 days. Anybody from our previous hackathon participants? I think some of you might know this one. Anybody who has done hackathons in the past with VSD? With VSD? Oh yeah, there are a couple of previous participants. Okay, good. So close to 30 teams had joined, and they were selected as a part of the second level. Out of 30 teams, 10 teams, the 10 teams made it to IIT Madras. Can I request all the 10 teams to stand up over here? Anybody, where are the 10 teams who came yesterday? Okay, one team was here. Where are the other teams? So you can see all of them are spread across the crowd. Where are the other teams? The 3 teams are with me. And there is one more team over here. Yeah, you can stand up. And who all? So if you see this, just wave to everybody, just like you're an actor, Yeah. So these are the teams. So if you can ask me, these are the teams from the top 70 teams out of India who were selected for the first RISC-V based hackathon at IIT Madras. These guys deserve a big round of applause. Anybody? So today, whoever out of the 10, the prizes are for top 3 teams, but whoever are present over here, the top 10 teams, they are all winners because you have mounted the whole thing. You have basically climbed the whole ladder that has been seen over here, and then you have made to IIT Madras. So there are prizes for everybody, but only top 3 is just for who was better than who. That is what it means. But for IIT Madras, for the DIR-V team, all of you are winners. Okay, so congratulations first of all of you. Okay, then there were 3 more teams from the SOC team. The 3 teams, can you just stand up from who have used the FPGA boards, the VSD FPGA boards for the core SOC team? They will be anyways will get felicitated later. Okay, so I think they might not be here. And by the way, for all of you, the products are all displayed in the stall area. If you want to look into what did they do as a part of the hackathon, you can look into their products in the stall area. So it is all set up over there. Out of the 10 teams, now even the 10 teams who are present over here, they don't know who are the top 3 teams. But the top 3 teams is something which we are going to announce in few minutes from now. And the prizes will be distributed towards the end of this particular event. And the top 3 teams today are going to show their working demo. So we are going to call each and every the 3 teams one by one, not in the right order. Even the teams doesn't know who is first, who is second, and who is third. We'll call them in random order. They will present their work over here. So since all of you are students, you can take an inspiration from them and try to build products. Try to focus your education towards products. So that is how these teams actually came up with the final demo. So the top 3 teams will be called in some time. But before that, we should not forget to recognize the entire team who was behind us in this entire 45 days of event. So first round of applause goes to Professor Kamakoti. He is not there, but he will be coming today evening. So just make sure all of you attend his talk in the evening. He's a very inspirational person, very motivating person, and he was the one who actually motivated the whole team. We are all because we have been working with him for close to 7 to 8 years, and it's all because of his motivation that India is now at this particular position. So thanks to Professor Kamakoti. Don't miss his lecture. Second is Rutra Murthy. I think all of you just met Rutra. He was somewhere over here. Where is Rutra? Rutra, can you just? He's the main guy. Where is Rutra? Rutra Murthy. Okay, he's outside. So Rutra is he's the beam. He's the beam of our team. he makes things. He makes sure that things are basically arranged in the right way. Things are moving properly in the right way. So that's what Rutra. So yeah, the one who was hosting before me, he is basically Rutra Murthy. So all of you, when he comes back, just make sure you clap for him also. Okay. Second is Lavanya. So Lavanya was the Arjun of our team. So Lavanya just wave, just like an actor over here. So she is Lavanya. So she was the main one. So right now, all of you, if you're seated over here, if you're seated at this particular location, that's because of this kind lady over here. She's very kind by heart, but she must have bugged you that registration is not available, this not available. But she's the main person. Okay. So Lavanya, thanks for your time. Sharad Kaul, I don't know whether Sharad Kaul has come over here, but he was also the one who actually started this whole event. He was there. He's from Keynes Technology. He was there in the whole event from the beginning. So Sharad Kaul, maybe when he comes, I will introduce all of you. Oh yeah, so there is Rutra. So cameraman can just focus on Rutra. So he's the main guy. He's the beam of our team. He is the one who made things happen. So yeah, he will be very much visible on the camera right now in the blue. He's looking very smart today in the blue. Yeah, so that's Rutra. Rutra just wave like an actor. Okay, next we have on the team, on the dice we have, where is the slides? So Gopinath was the one who basically arranged. Gopinath, can you just quickly stand up? And so he's the one, Gopinath is the one who basically arranged the entire hackathon event, from start to end. He's the one who managed the whole thing. So Gopinath is he's the guy. He was the one who managed the whole activity for the product level hackathon. And finally, we can go back to the main screen.
Okay.
And we have Kunal. Yeah, Kunal, that's me. Like a year ago photo. Yeah, that's me. Okay, hi. Okay, next, and we have Anagha. Anagha, the one who was again from the organizing team. She's right over here. Just quickly on the stage. Yeah, she's Anagha. Okay, so now let's go on with the event. So the first, we are going to call all the colleges one by one. So all the colleges, I think all of you are instructed. You will have 5 minutes to demonstrate your work. So let me call upon the team from Sri Ishwar College of Engineering, IoT powered smart home automation system. And can I welcome all the team on the stage with the demo? All right, yeah, please welcome Sri Ishwar College of Engineering team, Lumicore, and yeah. Don't go by her height, she's very smart. All right, yes, over to you.
A warm good morning, everyone. Today, we are here today to present you about our project Lumicore. Let me start with a question. How do we manage our homes? We switch on lights and fans on and off manually. We guess the air quality based on how we feel, and we detect gas leakages or fire only when it's too late. It's time consuming, inefficient, and sometimes even unsafe. In order to address this issue, we have developed our product Lumicore, which is a smart home automation system powered by IoT. This product can help you manage your homes in a more smarter and easier way. With Lumicore, you can automate lights and fans based on light levels and human movement. And also you can monitor humidity, temperature, and air quality in real time. And with that, you can also detect gas leakages and fires, and you can trigger immediate alerts. And last but not the least, you can monitor every information remotely using a web and a mobile app. So this product isn't just useful for homeowners. Elderly people and people with disabilities can also find it very useful and much helpful when they are not able to move around. And property owners who manage a lot of homes or buildings simultaneously will find it very helpful. And beyond homes, our product can also be extended to be used in hospitals, workplaces, and also educational institutions to increase the efficiency and convenience. Our product uses Vega RISC-V 3.0 development board, which uses RISC-V architecture. So RISC-V is an open source instruction set architecture which is used to design processes. And using our product, we can make our smart systems more reliable and more smarter. In future, we have planned to integrate artificial intelligence in our product to enhance the accuracy of the results, and also we can also prevent and avoid misleading results too. So our product doesn't only help you automate your home, but it also does it in a more efficient and in a convenient way.
Do you want to show the demo?
Yes, sir.
Yeah. How do we switch to this camera? Okay. Lights coming in. You can little bit lift it up like this. It is good. Okay. Just showcase them. What's happening? It's fine. It's fine. You can explain.
So here is a product, and we have an PIR sensor which is used to detect human movement based on IR radiation. So when a person, when the sensor detects a human movement, the lights will be switched on automatically. And then there is LDR sensor which we can use to switch on lights based on the light intensity levels in this room. For example, if there is darkness, the LDR will detect it and it will automatically switch on the lights. And then next we have the DHT11 sensor, which is used to monitor the temperature and humidity levels. It can we can further extend it to switch on air conditioners and other appliances based on the temperature. So we have used a flame sensor to detect fires, and once a fire or a flame is detected, it will trigger an immediate alarm which will alert the people in the surrounding to take necessary action.
Okay, so I have a question. How were you able to switch on the lighter so fast, you know? Tuck, tuck. Huh? Okay, it was a very good demo. And if you want to look into this demo, it's already there on the stall. So a round of applause for the team. So you all guys in which year?
Third year, sir.
Third year of engineering college. Okay. And you are from electronics background?
Yes, sir.
Okay, so you get a motivation over here for all the engineering students. So this is basically, you know, the thing that we are driving over here. It's basically called as product-based skilling kind of thing. The outcome of your learning program should be a product like this. That's what we are going to spread across India. That is the motivation behind Professor Kamakoti's vision, and that's what we will be doing across India over the next upcoming years. Thank you so much. Thank you so much for your time. Yeah, you can take it. And make sure it works at least for 2 days. Okay, so next is what all of you are waiting for. The snack lunch. No, it is not happening now. Just wait for 20 more minutes. So we are going to call the next team, which is PSG College of Technology, and their project is Energy Efficient System for Electrical Motors. Team, can you just come on the stage? Yes, so the project name is MotoGuard, and the college name is PSG. Yeah, please come. All three of you, yeah. Huh? Yeah, use this. Okay.
So, hello all. I am Harikrishna from PSG College of Technology. So, our product is MotoGuard, which is a fault detection and predictive maintenance specifically for electrical motors. So, why this product is featured? So, in all our industries, most of the electrical motors, in specific, 60 to 70% of the electrical loads are motors. So, insufficient usage of this motor and downtime of this motor will lead to more environmental and economical impact on the society. So, what we have built is, we have built a fault detection and predictive maintenance system for this electrical motor. So, our project will consist of various sensors to analyze the motor's performance, and RISC-V based microcontroller for analyzing the and processing the data of the motor. So why RISC-V? Since open source community, an emerging community, RISC-V is a very scalable and it provide various security. So we have, and also the main point is it's low cost. So we are using RISC-V microcontroller for this project. So what are the working of this project? First, the vibration data will be calculated by from the sensors, and the data which is processed in the RISC-V controllers will be given to fed to a cloud-based environment, where a predictive ML-based cloud computing model will predict the further fault in the motor, which will be very much useful in predicting the motor's performance in future. So let us see a demonstration. So as you can see, currently the motor is working. So when vibration is detected from the motor, you can see that vibration is analyzed from the motor, and the signal is sent to the microcontroller. And also we can see the performance and analytical graph in the cloud-based environment, where you can see that how three-dimensionally the motor is moving. So by this data, we can give this data to a ML-based computing model to predict the future purpose of the motor and future performance of the motor. So as I earlier mentioned, 60 to 70% of the industrial loads are motors. Inefficient usage of this motor will cause a severe fault, severe economical and environmental condition. To prevent this, we have been implemented this project. Thank you.
So you guys from which standard? Sorry, which standard? Which year?
Third year.
Third year engineering colleges. Yes. Oh, okay. Okay, good. We have got smart third year engineering students over here. Yeah, we can pass this. Thank you so much. So we have been running a lot of chip design for school programs where we have people from 6th standard to 12th standard. So I keep asking them in which standard you are in. It's been going for 3 months. Okay, so next let me invite Sri Satyasai Institute of Higher Learning team. Their project is dual axis solar tracker. So the team, are you guys here? Yeah, please come in.
Good morning, everyone. We have the product HelioSync 360, which is a dual-axis solar tracker. So why is solar tracker? The first question everyone asks is, in India, we use 90% installation system, which is a fixed tilt systems. So we want to replace it by a dual-axis solar tracker, so the efficiency will grow up and the power output should grow. So this is our product, HelioSync 360, which does the tracking system for the solar tracker. So wherever the sun goes, our sensor, which are LDR sensors we use, will track that and take the average from all the sensors and just put our HelioSync 360 towards the sun. And we can really track, and the power output will be very high as compared to the previous one, which is the fixed tilt systems. So we can have a demo if everyone can see that. Yes, so everyone can see it directly move towards the intensity which is the highest. So now we use a cell phone to just, yes. Can you use this phone? So what happens is we have 4 LDR sensors in it, and it takes the average of all the sensors. So after that, it'll take the average and it'll point towards the place wherever the intensity is the highest. So we are using the servo motors and the RISC-V architecture VSD Squadron mini board. We are taking the ADC pins and giving the pulse modulated pins. So yes, everyone can see that it's working. So about the scalability, we want to talk about that. This is very and highly scalable. It's very highly scalable because most of the systems in India is fixed tilt systems, and we can easily increase the scalability using that. Thank you.
Okay, so you guys are from which year? Third year, okay, mostly. So I think if all of the colleges are present over here, third year is the right place where we start product-based skilling for all the participants over here, right? Okay, good, thank you, that was an excellent demo. And I think yesterday what happened, the judges had asked a lot of questions about RISC-V, and most of them were not able to answer RISC-V, so I think all of you have studied well. We went through the David Patterson book and studied about RISC-V, I guess. Okay, good, so that was a good demo. And finally, we'll just conclude the whole thing. I'll go back to our slides. So most of you, I've been talking over here for last 20 minutes, and most of you might not know who we are. So we are an edtech company. We are mostly into building edtech solutions for semiconductor hardware learning. So just to explain who we are, I've just created one small demo video for all of you. I'll play it, and so that will give a clear idea about what VSD is all about. Okay, so I will play the video over here.
How will the future of semiconductor technology shape our world? This isn't just a question to ponder, it's a challenge to embrace. And at the forefront of this challenge stands VSD, an ed-tech company and a community-based technology aggregator shaping the future one chip at a time. Since its inception, VSD has been a trailblazer in the semiconductor field, not by reinventing the wheel, but by connecting the right resources, the right minds, and the right tools. That's where the magic happens. That's where creativity sparks innovation. Over the past decade, VSD has made significant strides in the open-source semiconductor domain. It has been the catalyst, the driving force behind the revolution in the VLSI design process. With a focus on developing high-quality training content, VSD has empowered students to design silicon-grade IPs and SoCs, and not just design, but also guide them through the intricate tape-out cycle via the Google Open Shuttle program. But VSD's contribution doesn't stop at education and guidance. The company has made EDA tools and design flow accessible to the community, breaking barriers and democratizing semiconductor design. The result? A vibrant community of innovators who have developed more than 52 analog and digital IPs and solutions. And of these, 19 have seen the light of day in silicon. Imagine that. 19 tangible physical manifestations of creativity and innovation, all thanks to a platform that believes in the power of community. But VSD's journey is far from over. The company continues to push the boundaries of what's possible in the semiconductor industry. Every day, it works tirelessly to bring about a community-based revolution. A revolution that's not about creating a divide between the haves and the have-nots, but about fostering a culture of inclusivity and collaboration. And as we look to the future, one thing is clear. The semiconductor industry is evolving, and VSD is leading that change, but it can't do it alone. So if you have a passion for semiconductor technology, if you want to be part of a revolution, VSD invites you. Join the VSD community. Help shape the future of semiconductor technology. After all, the future isn't just something to predict. It's something to shape, to mold, to create. And with VSD, you have the opportunity to do just that. Stay tuned. The best is yet to come.
Okay, so that's all from our side. And finally, I'll just take a quick selfie with all of you because I don't know whether we'll be meeting again or not. So just raise your hands so that I can capture all of you. Maybe I'll come in the center. All right, thank you so much. That's all from my side. Thank you, and we'll meet after the symposium. Thank you so much. Bye.
Thank you very much, Anaga Ghosh and Kunal Ghosh, for the wonderful presentation. I think எல்லாருமே காலையில சீக்கிரம் வந்துட்டீங்கன்னு நினைக்கிறேன். It's time for break. We'll have cup of coffee or tea. So I'll tell you how to go. So we are actually going for a tea break now. The tea will be provided in the 6th floor. Right now we are in the 7th floor. Once you go out of this auditorium, on your right hand side you will find steps கீழ இறங்கி போனீங்க அப்படினா it's a big hall where a lot of exhibition also happening, And exhibition ku pinnadi, we have the tea break setup, like tea setup. But you don't restrict to one counter. There are 6 counters. You can go around the exhibitions also, and then you can find the free slot, and then you have your tea, cup of coffee, and then we can meet here by 11:10. And once you're coming back, we will give you your diary and a pen to take notes and other things. Yeah? Thank you. You can keep your bags here. It's safe, so. Welcome back. May now request Ms. Lavanya from Vyoma Systems, who did this system software hackathon. I kindly request everyone to take your seats. The session will begin immediately. Lavanya, please take over.
Thank you, Rudra. Hi, everyone. A very good morning. On behalf of Digital India RISC-V team, we invite every one of you once again. And we will be starting the next track in the hackathon series. The track is System Software Hackathon. We will be giving an introduction, a brief introduction of what this means and the problem statement that was given to the students. It was facilitated, organized by NXP Semiconductors, our lead sponsor, along with MindGrow and Akiana. And we have Pravartak and Shakti team who have been helping us in the partners who have helped us in organizing this hackathon. So what is RISC-V? So this is Digital India RISC-V program. RISC-V is a reduced instruction set computer, and it's an open ISA. Unlike the proprietary ISA, it is license-free, and it is easier for us to use and explore the computer architecture domain. What is more key features for this RISC-V ISA? It is open source, it is modular. You will be hearing that everywhere today. It has been widely adopted because it is open source and easy to use it. Modular because based on the application domain, you will be able to take a subset or the full superset for your application needs. Customizable because you will be seeing a lot of startups who will be customizing the ISA for their own needs and the application that they are targeting. Community driven, you see us, you witness the whole host of industry major who facilitated this hackathon, the institute, the academic group, and the startup and the incubator who supported this hackathon series, as well as the Digital India program. We all come together as a community for having this Digital India RISC-V program today. A bit of a tech to start with. So this track is system software. Traditionally, we have heard in VLSI domain, we have hardware. Consider that as a big palace. But if you have only one door and access to only one room, then the whole palace is not used. So with that analogy, we know that the system software is the foundation layer that provides the efficient hardware-software integration, where it allows you to use the hardware that is available. Let's say it's multi-core, it's 1,000 cluster hardware you have in your hands. But the system software facilitates the use and makes sure that all your application on top of it runs very high speed and utilizes the performance of the hardware. And the system software libraries, the operating systems. If you want to be expert in system software, it means that you should be familiar with the device drivers, compilers, and system libraries and debuggers that are part of this whole package. So using that as the base, we had this hackathon done, where the participants, the teams across India were given a challenge to modify the system software. Traditionally, we will modify the hardware to make sure that it reaches high performance, but we switch the table so that the students get an opportunity to develop what it means to have a system software and how efficiently it brings in the performance. So the example benchmark that was used here was CoreMarks, and it was made to modify such that they get the opportunity to look at that. Why we did that is because the system software traditionally in the RISC-V has its own challenges, where it is not yet completely mature to use for all the extensions that are available in RISC-V. It requires efforts in building the ecosystem maturity. It also requires toolchain support for varied applications that we are using it for. There is also variability, as I mentioned. Everybody can use the RISC-V in their own way, but in order to make that happen, system software plays an important role. So these are the challenges that are present for RISC-V itself. In order to give that exposure to the students and build that as opportunities. So where there is work, where there is pain, there is an opportunity to learn, become an expert, and use them for building the community, right? So that is the intention behind this track, where we have the hardware, we have the user application, the system software experience or expertise that has to be built was something that we gave a flavor for the participants. Next slide. So in this, we had a webinar. We introduced our structure, the background knowledge that was needed to go through the hackathon. And then the students were able to go through and research all the open source ecosystem that is available in software. And they were able to submit the final report by having the challenge where they will modify the system software itself. Let's go back to the interesting part. So this is the tech round. So next slide. This is the setup that we had given it to the hackathon people, where they use our cloud-based ecosystem environment, where the problem statement and the setup was developed. And Shakti's C class was provided as a base for them to play around. Next slide. So these were the top finalists who you will be witnessing here. Their stalls will be put up in the stall area, where they will be also presenting to you the challenges or the experience of their hackathon. I kindly request the teams to stand up so that people recognize you when they are going to talk to you. So these are the young engineers who have come. I would let them self-introduce when they are going to present, but these are the engineers as young as second year BTech who was able to handle the complexity of the system software that is as part of this challenge, and they were able to successfully participate in it. Next slide. And we have selected the 3 top teams who will be presenting to you. Soham, Suman, Dhruv from S.J. Sangvi College of Engineering. A round of applause, please. Mahati and Aishwarya from Nitya Meenakshi Institute of Technology. And Arna from IIT Varanasi. So I'll let them self-introduce and provide their experience in the subsequent slides. Thank you.
Good morning, everyone. I'm Soham Lotlikar from DJ Sangvi College of Engineering. We are third-year electronics students. So I'll give a quick introduction of what our problem statement was. We had to optimize and improve the CoreMark source code. So I'll show you the results, what we got. We improved our performance score from 2.31 iterations per second to a 3.35. And we reduced our memory from 223 KB to 173 KB. These are the flags that we used. We used an aggressive optimizer flag O3, and for the memory, we used an O1 flag. I'm not talking about the flags much because we have changed the code, which improved our performance significantly. So to talk about the performance optimization part of it, I'll call upon Suman.
Hello all. So coming to performance optimizations, for the state machines, we have used go-to statements rather than the switch cases because it has two benefits. One being it reduces branch mispredictions, and the second being that it eliminates switch overheads. That we are basically eliminating the need for a state variable, which reduces the instructions for the assembly. The next being that. The CRC U8 function, we notice that there are redundant variables and there's a redundant conditional branch as well. Next slide. We have also removed, we noticed that the C instruction set, while it has its uses. Oh, hello. Yes, so we've noticed while the C instruction set has its uses in the embedded world, here it decreases the performance ever so slightly. Essentially, it's basically because the C instruction set is a 16-bit instruction, and before being fetched or executed, it has to be extended to 32-bit, which adds a latency. The next being variable typecasting. This is one of the more common problems in 64-bit machines running a 32-bit architecture, 32-bit program, is that it has to extend 32-bit instructions to 64-bit, which again, as mentioned before, it adds latency. And then inline assembly, we have noticed that the compiler has weak operations. It doesn't take the optimal instruction. It doesn't use the optimal instructions to perform the operations. So we have added inline assembly to make it more optimized. The loop unrolling, we have used loop unrolling. It essentially branching. The branching instruction is a very expensive instruction. Is a very expensive instruction. So to eliminate that, we have unrolled a few loops. Hello, can you guys hear me? Right? Yeah. So for loop unrolling, the CPU spends less time on conditionals and reduces the branching instruction. Next slide being cache alignments. This is a very famous way to, or a more popular way to optimize C programs, is to align cache. This makes the variables more accessible to the program. Next, I'll have Dhruv talk about memory optimizations.
So getting to the memory optimizations, we started by analyzing the codedump.dump file which was generated. And our main goal was to notice if there are any instances which weren't really necessary. So the main instance that we found was in the core matrix.c file. A lot of the functions were being called again and again. So we decided to inline it. But when we used a flag, the memory really went short up. So we decided to individually static inline all of the matrix function, thus reducing our memory drastically. Moving on, we moved to the RISC-V else strip. It was a function that removed all the debugging features of our ELF file, and it also stripped all the unnecessary symbols present in our functions. Further changes, we looked into this function quite later into our development. This is a function which is not currently present into our system, but this is something we looked into. So the isDigit function. Sorry. So the isDigit function, the condition that is used has two comparisons, but it can be reduced down to a single zero offset, giving us the same result and optimizing our memory even more. Next slide. Apart from that, that would be all from our side regarding our system software optimization. Thank you to all the organizers for this amazing experience. Thank you very much.
Yeah, you can ask. Please go. So the question is, for the interest of audience, how much unrolling was necessary on top of what the standard compiler provides? I'll let them answer.
Right, this is based on trial and error, so everything is true what we've said right here. We've unrolled a few loops based on there's a trade-off between code size and performance. So we've unlooped just enough loops that the code size doesn't increase exponentially and the performance is also significantly increased.
She's asking a number.
Sorry, the number, as in?
Like how much percentage?
I think by 0.1 or 0.2.
Thank you. We'll call in the next participant or the next top 3. So we are evaluating them. You can also talk with them. So the prize is for them and the ranking will be done in the evening. So the next finalist is Arnav. He is the second year BTech. I'll let him self-introduce and then continue.
Check. Good evening, everyone. My name is Arnav Pahuja, and I'm a second-year electrical engineering student at IIT BHU Varanasi. And I'm here today to present my solution for the Systems and Software Hackathon. Improving the 2 baseline metrics, the core marks iterations per second, and the total time taken by the program, my final score was 3.46 iterations per second, up from about 2.31 iterations per second, and a total time of 11.5 seconds, down from 17.2 seconds, and I was able to get my program running 33% faster on the Shakti processor. So I followed a very systematic approach comprising mainly of 4 steps. First, I profiled the core marks program to identify performance bottlenecks and scope for improvement. Second, I refined the source code, improved the algorithm, and eliminated redundant operations in the matrix, state machine, and linked list functions. Third, I integrated extended assembly after inspecting the dump file to cut down the overhead. And fourth, I introduced GCC optimization flags to gain performance boosts during compiling. As you can see, most of my gain, about 62%, was in the matrix functions, and another 35% coming from GCC flags. Here you will see that the linked list and state machines contribution is about 1 to 3%, but this is not accurately represented because writing better code for the linked list and state machines allows the compiler to optimize the code even further, so that is counted in the GCC flags also. As you can see in the breakdown, after doing source modifications, we gain about 25% of the total boost. So coming to the first step, profiling the program, profiling reveals to us the most called functions in the call graph and the most time-consuming functions in the flat profile. This helps us avoid premature optimization and gives us functions in which even incremental gains will pay off in the long run. So key functions over here, core state transition, the state machine, core, the matrix multiplication and bit extraction operations, and the linked list sorting function. Second step, refining the source code. Starting with the matrix function, this matrix function multiplies 2 matrices together and extracts the bits from each multiplication and stores the result. So here I had 2 findings. One, that the result of this function was not being used anywhere after this function, and even then, only the sum value of this matrix was being used to calculate a verification value, which would verify the correct operation of the function, of the program. So, and second, I can skip all these multiplications and still get the verification value done right. And so that's what I do over here. I do a very rudimentary basic operation to skip all, to just satisfy the verification conditions and skip all those tedious 3 nested for loops, ONQ process, and gain a huge performance boost. All other functions of the matrix operations were doing identical operations on all the elements of the matrix. What I did was they were doing iterating to all elements of the matrix using 2 loop variables, 0 to n, 0 to n. And what I did was I used only 1 loop variable, flattened the matrix out, and serially indexed it, going from 0 to n square. So that's what I did, and I gained about 62% of performance boost from matrix operations, 2.5 seconds in the bit extraction operation. Coming to the state machine, I noticed that there were intermediate states that did not affect the final output of the state machine. So what I did, I introduced a look-ahead byte, which points to the next input coming after the current one. And whenever the state machine tries to fall into these intermediate states, I immediately check for the next, for the future conditions of the look-ahead byte, and immediately skip to the next state it is trying to go to. With this, we save the for increment, loop variable increment and check, break condition check, and also the switch operation. So we save this code in the best case, and here we are trading memory usage for performance, and very small gains over here, but as I said, it allows the compiler to optimize it even more and counts that in GCC flags. And so direct state assignment over here. Next, coming to extended assembly integration, I noticed that there were little functions doing operations like checking if a byte is a digit in a sky value. So this, I I devised a new algorithm which sacrificed checking for some edge cases, but still worked on the code. And this is yet another trade-off, but I could reduce the instruction count from 4 to 3. And another function for linked list sorting, which reduced 4 instructions per function call, using other operations like unsigned load and logical shift instead of arithmetic shifts. And so what I found out was directly integrating this extended assembly code into the program leads to a huge performance drop in contrast. This is because the assembly code to the compiler is like a black box, which it cannot optimize further. It cannot see through. Every time it comes to this block, it has to execute all these instructions. And writing, that's why it leads to a huge performance drop. What you can do, what I found out was a solution to write better and clearer C code, which expresses the same ideas and compiles to the equivalent assembly, so that the compiler can also optimize and we can get the GCC performance optimization flags boost, which made our final program run 10% faster, my final program run 10% faster, and accounts for 35% of the total gain, about 23% of it coming after doing the source changes, after writing the better and clearer C code. I did aggressive inlining optimizations, loop and floating point optimizations. For the code size reduction, I used a standard GCC flags, which sacrificed execution speed for reducing code size, and reduced memory accesses and increased register efficiency. I also used a machine-dependent RISC-V flag, which fine-tuned for smaller code size on a RISC-V target. That is it. I got a 12.6% code size reduction, and thank you.
Any questions? Thank you. Thanks, Arna.
Thank you, ma'am.
We'll have the next team presenting their own results. So it is for both performance optimization and code size reduction for core marks.
Hi guys, I'm Mahati. We are from Neti Meenakshi Institute of Technology, Bangalore. We are third year engineering students, and the main problem statement was divided into 2 parts. The primary one was performance optimization and the other one was memory optimization. My friend here will brief you about the performance optimizations and the key changes we made.
Hello everyone, I'm Aishwarya. I'm here to talk about the first challenge of the hackathon, that is performance optimization. Here we aim to improvise the execution speed, the throughput, and the RISC efficiency using the Comark execution on the Shakti processor. We've made a series of changes. Let's start with the makefile changes. We've made some tweaks to the compiler flags such as O3, fun roll loops, and FLTO for better execution flow and for instruction execution. As you can see, we have brought down the execution time by 11.45%. Next, matrix.c changes. We've leveraged local accumulation and also replaced the function calls by direct bitwise operations. Next, portme.h changes. As you can see, we've disabled the stdio library for unnecessary dependencies. That helped us for lower latency and better execution. The major set of changes we made were in these 2 files. The core list join.c. Here we've focused on functions like calc function, core list merge sort, core list bench list for better CRC calculations, and this helped us to reduce the total ticks and iterations per second. Coremark.h, we basically focused on one main parameter, that was total data size. We brought it down from 2000 to 400, which helped us in reducing the total ticks by 96%. As you can see, this is a graph to show the performance improvements we've made. We brought down the core mark size from 666 to 133. That's a decrease of 80%. And the other 2 parameters are total ticks and total time that have been brought down by 96%. And the iterations per second was brought from 2.3 seconds to 57.7 seconds.
The second challenge was the memory optimization challenge. An efficient parameter to measure this memory optimization challenge was checking the number of lines in our dump file code. The lesser the size of the dump file, the better memory efficiency we have. To ensure this, we've made 3 key changes. First was the data size change. we've reduced the total data size from 2000 to around 400. This reduced our total lines of code by around 156 lines. This showed that we could have a lower memory footprint and also improved benchmarking. The second change we made was in the make file. We changed optimization flag from O2 to O3 for our performance optimization, whereas here we've changed it to OS for smaller binary size. We've enabled link time optimization like FLTO. We have used various functions like fdata sections and fdata functions to remove all the unused code in this. This has reduced our total number of lines by around 900 lines. The key change we made was in the makefile core mark section. Here we've used two very important things. One was object dump, so that we only dumped the relevant sections like .text and .data into our dump file. The second was using a technique called binary stripping, where we used it to remove all the debugging symbols and reduce the size. Here you can see that our total number of lines were reduced from 4,620 to just about 758 lines. This means a total change of around 84%, and the major change we acquired was from our change 3, where we changed the core mark file, which contributed to around 78% of the major change. We thank you for your time. If you have any questions, you can please ask them now.
Thanks one and all for having seen this. The stalls, they will be available in the stalls along with the other finalists of this hackathon. If you want, you can interact with them more. Thank you. So we will move on to the next track. I invite Bala. I'll start with he's our ex-IITM student. After that, I'll let him self-introduce and his team. So he leads the core enhancement track. Over to you, Bala.
Hi everyone. So I will be talking about this core or SOC. Can you hear me? Okay. So yeah, I will be talking about core SOC design enhancement track. So a little bit about Redwood EDA and company. So we do some technologies. What we primarily focus is on better modeling technology. So we do have something called TL Verilog, which is transaction level Verilog, which is like little abstracted layer over traditional Verilog methods. So how we do RTL based methodology. So this is like in transaction level. So the participants were using TL Verilog for this hackathon. So and also Redwood EDA offers tools with better user experience. They have a platform called MakerChip, with which in web platform you can run design in Verilog or TL Verilog, whichever. You can see the waveform, you can visualize what the design is happening, and much more tools. Yeah, and also we have some AI assistance along with it, and the things which are happening in MakerChip, Redwood EDA, TL Verilog are entirely open source. So this is about the platform that I was mentioning. So if you see, like, we have editor view where we can write the Verilog or TL Verilog, whichever language you prefer. You can see the right one is the visualization part. So we do have some kind of virtual FPGAs. So whatever you see, and if you want to see in action what is happening in an FPGA, you can see visualize over there. So it's not an exact visual FPGA which is running in the background, but we have simulated the environment. So you can see it live in action. And we do offer some diagrams, so we can see how the hierarchies, how the code is written. It will be easier to analyze. And finally, waveforms, traditional view. And yeah, and I will go through the track. So the objective of this track is to work on some ML inference. So on resource-constrained devices. So we use the hardware, software, code design approaches. Primary focus we covered is to design a systolic array. So and then we do some kind of workload optimization by using CPU plus accelerator kind of hardware software core design, and we see how much compute and bottlenecks happening, and then how better it is performing if you do the CPU plus accelerator system. We'll see the difference between CPU and CPU plus accelerator system. That's the primary objective of this track. Yeah, problem statement, if I want to explore further, to design a systolic matrix multiplication in TL Verilog. So user can choose whichever architecture that they want. Primary architectures are output stationary, input stationary, weight stationary. They can do their own data flow also. And finally, they have to support fully connected and con 2D layers, basically convolution operations in makerchip.com. And the implementation part, so just to compare between how the difference is from CPU and CPU plus FPGA combination, they will be writing a simple C code, same operation for convolution, see how it is performing when you run only in CPU, and then they will deploy the accelerator on BSD Squadron's FPGA. So it's an I-40 FPGA that they have used. It's a very small FPGA, very low cost. And the primary objective here is we have to fit into that FPGA. So they have to be like very constrained in that. And see the work optimization that they got, like what are the benefits, memory, compute efficiency on the CPU plus this FPGA accelerator system. Timelines, yeah, so it was a 1 month period. Yeah. Stage 0 is like ramping up of technologies, basically TL Verilog, and started coding. Stage 1 is design submission, and once we selected around 10 participants to stage 2, and for those participants we shipped the FPGA boards, VST Squadron's FPGA board to them, and then implementation phase, it goes for like 2 weeks, and once it's done, 3 participants were selected out of it, and final demo they will be showcasing now. And yeah, as far as evaluation, we were checking for the functionality, how the correctness of the systolic array implementation, and optimization like performance improvements, like what additional stuff they have done to improve the performance of the accelerator, and any other innovations, novel strategies and enhancements. Now I will go quickly give it to the teams. Team 1. Yeah.
So, good morning everyone. Myself Mithun Kumar, he is Preetham, we are from IIT Bombay. So, as you our problem was to make a systolic array accelerator for matrix multiplication. So, first we have written the systolic array code in TL Verilog, and also for optimization purposes, we implemented a Wallace tree adder and a Kogistone adder to minimize the timing, the clock frequency. So, coming to the architecture, we chose a weight stationary model for the systolic array. The reason for choosing a weight stationary model is to, during the inference phase of AI models, mostly the weights are stationary, like we don't change the weights. So, it will minimize the amount of memory calls, thereby increasing the performance. And also, we used UART for the communication between laptop and the FPGA board to showcase the final results. We have successfully demonstrated a matrix multiplication, and the correct values were observed using the UART terminal. And then to compare the performance, first we implemented a conv2d function in simple C code, and we have simulated it using a RISC-V simulator. The CPU was a 5-stage RV32IM CPU. So the cycles observed were 7,534 cycles, and then we dumped our systolic array code on the FPGA and measured the cycles. So the computation took 24 cycles, and the data transfer, the loading of image and weight matrices and storing of the output matrices took 458 cycles. So in total, it took 482 cycles. So we can observe that there is a 15 times performance increase in by using the systolic array. So that's it. Thank you.
Thank you. Any questions you have for them? Okay, all right. Thanks. Thanks. And team 2. Yeah.
So, hello everybody. I'm Indra from SSN College of Engineering, and my teammate Arvind, he is also from SSN College of Engineering. So, this is going to be technical, but I don't want to bore you, so we will try our best to make this interesting. So, do anyone know any ML accelerator product names? Like from NVIDIA, Google TPUs. So, NVIDIA, they have CUDA, right? So, do anyone think about what challenge they are facing? Like, anybody? So, I want this to be interactive, so. Yes? Okay, cost, but I'm asking in terms of software, like computation power, efficiency, like that. Okay, so the main challenge all the ML accelerator people, designing people are facing is computation power and efficiency. So, in this objective, okay, let's take an example, convolution. So, basically a convolution demands more processing power. So, for this processing power, basically we all studied convolution using a basic matrix multiplication, right? So, as in this objective, we are going to do the convolution using systolic array multiplier. So, what's the difference between this basic matrix multiplication and systolic array multiplier is nothing but in basic matrix multiplication, we will just multiply all the rows and columns, which is not parallel. When it comes to systolic array multiplier, you will multiply all the image values and kernel values, which will done parallelly. So that's a systolic array multiplier. I don't want to go much deeper into it. So next, now our main objective is we need to accelerate this convolution, 2D convolution, so that we can reduce the number of clock cycles. For example, if you do the basic matrix multiplication for the convolution, it will take more number of cycles, so you will consume more hardware. If you use systolic array multiplier, it will reduce the number of cycles. Okay, so we need to prove if you use the accelerator and if you do the convolution, we are reducing the number of cycles. So that's the main objective. Okay, so they given us TL Verilog. So for the people who doesn't know what is TL Verilog is, we all know Verilog and system Verilog. And the TL Verilog is a transaction level Verilog, which is an abstract level of Verilog. And for example, if you are designing a counter in a Verilog, you will write about 10 lines of code or more than 10 lines of code. When it comes to TL Verilog, it is one line, it's finished. So yeah, it's a new language which is found by Steve Hoover, Redwood EDA. So we are using the TL Verilog, we design a systolic array multiplier. So in systolic array multiplier, as I told, it is a parallelism. So first you need a processing elements, and each processing element will do a multiplication like a one row, one column like that, and each processing element will store the outputs and it will done parallelly. For example, this is a processing element and this is a pipelining. For this, I will give you an analogy. For example, in a factory, there are n number of machines, okay? Each machine will do a particular task, and once there is a conveyor belt, it will place the objects. So here, each machines will be a processing element and these conveyor belt will be a pipelining. This pipelining will happen in parallelly and each processing element will do the process, okay? So this is a systolic array, and okay, so I told you we are going to reduce the number of cycles. So first we need something to compare, right? So basic CPU, which is doing basic convolution using matrix multiplication, that is one, that is without accelerator, and with accelerator we are going to calculate 1 cycles. So this is without accelerator, that is we write a code in C for the basic convolution, and we convert it into assembly language, and we use this software called VARP, which is a RISC-V 32 CPU simulator. So if you paste this assembly code, it will tell you how many number of cycles it took. So totally it took 198 cycles, which is without accelerator. So this is a basic convolution. Without accelerator is 198 cycles. And next, we are moving into image to call transformation, which is we are going to deploy this accelerator in this FPGA VAC Squadron FM. Okay, so before deploying into the FPGA, we are going to do some simulation. So we are going to check the output. Once if the output is correct, we are going to deploy in FPGA. So okay, so before deploying into FPGA, we need to improve the efficiency. So we are going to do image to call transformation. Image to call transformation we all know because, for example, if we got an image 3 cross 3, and if we got the kernel as 2 cross 2, the image to call will do like, it will convert all the rows into columns, and the kernel 2 cross 2 will be converted into 4 cross 1. So if we do so, it will improve the efficiency. So while doing, we got the output. This is using to improve the efficiency. And next, I will give over to Arvind to explain about the cycles which we got in another simulator.
So basically, we developed a C++ code to calculate the amount of cycles. So we did IM to call and GEMM operations to perform the matrix multiplication and convolution process. So we used QEMU simulator to get the amount of cycles. So we have also did the tiling process. So we did tiling process because if the input is if the given input is like bigger than the memory size of the FPGA, so we can divide the input so that we can tile it and then we can do the process. So we have simulated the tiling process also. So here the input size is like 5 cross 5 matrix, and then the kernel is like 2 cross 2 matrix. So what we did was we just set the tiling size as 3. So the first tile will have the matrix like 1, 2, 3, 6, 7, 8, 11, 12, 13. And then the next tile will have 3, 4, 5, 8, 9, 10, 13, 14, 15. So this layer will act as the overlapping layer. So with this tiling process, we are able to perform the convolution more efficiently. Also, if a bigger input is given, we can manage it without any errors. So with the QEMU simulator, tiling, IM to call and GEMM process, we got that output. So from this, we can see that tiling process is very efficient in handling the bigger inputs. And then we got the output. Over to Indra.
So once we got the output based on simulation, now it's time to deploy in FPGA. So we deploy in FPGA using a UART terminal called Picocom, and we got the output, right now it is in a binary output. So what our plan is, like while deploying into FPGA, we plan like we will give the input like 40 bytes. The first 32 bytes will be for the image and last 8 bytes will be for the kernel. So after giving it, we got the output. So which is a partial output, and we can tell that by theoretical computation, we can say, for example, basic 100 megahertz FPGA accelerator will have around, they will set the clock as 5, and for if you want, this FPGA is 12 megahertz clock frequency, so we can set it up as a 41.67 seconds as a clock. So by using those theoretical calculation, we conclude that it is reduced 40%. For example, if you are using an accelerator, if you are using a systolic array multiplier and you are doing a convolution, it will reduce, so by 40%. For example, without accelerator and you are doing a convolution, for example, if you get 1500 cycles, and if you are using a systolic array multiplier and if you are doing the convolution, it will reduce to 600 cycles. So yeah, that's all. And this is done by the TL-Verilog, and this is in WARP software, and this is EDA Playground, and this is QEMU, which is Quick Emulator, and this is the basic Picocom UART terminal. Thank you. And also thank you for all the organizers, and especially Kunal Ghosh for shipping this beautiful VAC Squadron FM to her hand, and also Bala Dinesh sir and Sri Anna who give a lot of guidance while doing this, and thank you for them, and thank you for the audience for keeping listening to this. Thank you.
Yeah, thank you so much, Indra, Adit Shankar, and Arvind. Now moving to the third team. Yeah.
So a very good afternoon to everyone. So this is Anushka Tripathi. So presently I'm a student at Sri Ramdev Baba College of Engineering and Management. So in this hackathon, we implemented systolic array with TL Verilog on Makerchip IDE, and then we converted that to Verilog, and we implemented that on FPGA. We explored the open source FPGA tools like Yosys, and then we and so this is our team. This is Sandeepan Roy, and he worked.
Good afternoon, everyone. So we started with TL Verilog, since it's a new thing for a new language methodology for us. As introduced by Dinesh, that it's an extension to Verilog. We found this interesting that we did not have to write much lines of code just to implement our systolic array. If we compare that with just a Verilog or a system Verilog code, we have to write a module which could define a processing array, how it is going to process in every in any positive edge of a cycle. We just had to implement a pipeline here, which could infer as operations at the positive edge of the clock. So TL Verilog helped us with more abstract level of writing codes. It does, so the flow goes along that there is a tool by Sandpiper, which is again provided by Redwood EDA. So the tool takes the TL Verilog code, converts that to Verilog, which we as users can see the converted code, which the designers can figure out whether it suffices their need for the part of the design, and then it is simulated by Verilator, and one can visualize their code with a block diagram as well as the graphics, which can help them understand how the program works. So from our first stage, we implemented an 8x4 systolic array, 8 being the number of rows where we're supposed to feed inputs, and 4 columns for the weight matrix to actually contribute an 8 number of 4x4 matrix multiplication. So for the second stage, we had to write a C code where we were supposed to implement 2D convolution, which is the same functionality provided by TensorFlow library. First, we had few function calls to declare how we are working. As a part of our task, we were supposed to determine the number of cycles consumed by the post-processing process, and then to determine the number of cycles taken by consumed by the systolic array for the matrix multiplication. What we did is flatten the matrix across so that we can have a faster matrix multiplication, and our systolic array is basically an output stationary systolic array. We chose this so that every processing element could contain the result of the multiplication we wanted to, and then we could fetch as a part of the post-processing and add those values together with the bias value to get our result. So if we look at the as per the criterion, we had to go for an int8 precision format, which means the processing elements are supposed to process 2 8-bit multiplication. We first started with that. With stage 1, we went through the systolic array code on TL Verilog. Second stage, along with C, and then we had the VSG Squadron FPGA. It's again a new FPGA for us. We had to explore the architecture and to explore ways of implementing our design. We would dump the code, and for providing the inputs via weights and the weights and activation, we had to dump the memory on dump the values on SRAM individually, and then pass on the values in every cycle. And we had to follow the systolic array operation, which actually we had to pass the values imitating the systolic array operation, that not every value is to be passed on every clock cycle. Since systolic array does not fetch a value, it works on a systole operation. So the values are to be passed in the manner where the processing element is supposed to, the specific processing element is supposed to process the specific order of multiplication. Since it does multiply and accumulate operation, if we do not want to store a specific result, we have to feed 0, which we did, and we got our results. So we used DIR-V simulator to check the number of cycles consumed by our pre-processing, which came out to be 203 cycles, and by 16 or 17 cycles, we were able to extract the complete output of one iteration in our systolic array. That's how we came across this. That's how we learned TL Verilog. So through this track, we got to learn a lot through this, and we have plans for working on accelerator designs based on the CNN applications on systolic array. Thank you, everyone.
Thank you so much. Up for questions, anyone? Okay, thank you. All right, thank you so much again. Yeah, that's it from this track. I think I'll move over to the FPGA systems track, Chakra Innovations. Yeah, thanks a lot.
Good afternoon, everyone. So all the hackathons that you just saw are mainly were run online. So this was the only hackathon that ran online as well as offline to nearly 48 hours. The volunteers, organizers, they didn't sleep for more than 3 nights. So as my voice also is gone. So this, yeah, welcome all. So this is the one of its first kind, which we attempted from as part of Shakti, as part of Chakra. We wanted to take an attempt of doing this. This is the hackathon majorly targeting for the industry as a product. We wanted to prove Shakti is capable on bringing up a product which is of industry standard. So yeah, myself Gopi from Chakra Innovations. I'm the CEO co-founder as well as working with Shakti as well. So yeah, this hackathon is basically to, as I said, to promote Shakti's adoption majorly in automation, logistics, and industrial applications. So if you see the problem statement that we gave, that will be coming in the next 2 slides, are majorly the very commonly used in industry. Gadgets as well. See, processor is mainly, if you see processor are mainly used, what do you see in mobiles and laptops and desktops, that's one is commonly seen. But if you see in the whole auditorium, other than your mobiles and laptops, there are more than 10,000 processors, variants are there. For example, in this mic, for example, in the speaker, the audio system, everywhere. So it's not, you need a compute intensive processor everywhere. You can have a processor which is not compute intensive, but it gives you it can solve your problem, like your washing machine. So that's what we wanted to take up Shakti on such a problem, give such a problem statement and cater its application. So yeah, majorly it is organized by us, Chakra Innovation. We are one of the DIR-V startups incubated at IITM Pravartak right now. Our majorly we focus on bringing up IoT products using RISC-V core. So yeah, you could visit our stall that's there. We will be happy to give you more on that. So what we did is the 2 problem statements that is going to be coming next is should be done using this Nexus FPGA video board. So this Nexus board is an FPGA where they need to dump the bit stream of Shakti SOC. So the SOC peripheral components are listed here. This is the default SOC that we gave, as well as we gave them the customized which they want. For example, they wanted a GPIO of 20 number, which was there actually. So we were able to give that, we were able to generate that. And all these were done to, for the past 2 months, we did 2 to 3 webinars online. We were able to help them out on their queries. The only condition that we set for this hackathon is, we will be only be able to give you the board alone, the FPGA board alone. All the components, everything that you have to bring here. And the problem is when they bring the components, if there is an issue with the components, they have to deal in that 48-hour only. So that's the major challenge that they were facing also. Yeah, we'll go to the next slide. So this is the first problem statement, which is a robotic arm. This arm is basically to sort balls. If you see in industry, there will be automation in sorting things. If they wanted to sort some milk products are coming there, they need to pick up the right one and move out. All these sorting algorithms is needed. So on the same test case, we wanted to bring up a robotic arm and basically to sort 3 different colors, red, yellow and blue. And the robotic arm has to pick from a bin which has all the balls and identify that color and put it in the correct bin. So this is the problem that first problem statement. Next. So the second problem statement is a very commonly competition that everyone of our industry usually attends, like problem. I mean, it's a maze solving. You have to. So this is not exactly like a micro mouse. This is like you have to find the obstacle and find the correct way. That's the only thing was. So this is the second problem statement, and this was the condition that we gave, that the maze should be a maze that we are going to give you will be having 3 meter by 3 meter. So all these things was just told to them. They need to, with this specification, they need to come up with a solution. And especially for this problem statement, we in the hackathon hall we were having a room of 3 cross 3, and we made a maze, literally 3 cross 3 meter cross 3 meter. We made a maze overnight, and that was not revealed to the participants. It was closed and it was kept locked. And there is a small maze for them to train their bots and get used to it. So if they are getting used to it without hitting the walls, they will be able to get into the main maze. So that was, we have videos also to share with you, because see, other hackathons, then they will be able to show you something here, but we can't bring up a maze here or something. So we have a video compilation that happened. I can share with you once this is done. So yeah, next. Yeah, so a round of applause for this finalist, top 3 finalists. Around 70 registrations, 70 teams for this particular track got registered. In that, we asked them to submit a proposal announcing these 2 tracks. We asked them to submit a proposal. In that, 33 proposals came, and among the 33, it was really a challenging for us to bring the best ones. Because most of them, the proposals, most of them, around 60% of the proposals were good, but we wanted to select the best one because we know that it is going to happen 48 hours, nearly 48 hours, and we will have to assist them, help them, all logistics, everything was there in our head. So we wanted to shrink as much as possible, and we selected 13 teams. In that 13 teams that they went through, last 2 nights went through all those things with the 13 teams, and these are the 3 top teams they have got selected. And the first, second, third will be announced in the evening. Again, a big round of applause for them. Yeah, I request Mosphere from SSN Engineering College, Ajiti, Sriram and Vinit to present first. I wanted to read out the next two teams also. The team name is Falcons from Banariam Institute of Technology, BITS from Coimbatore in Coimbatore, and the names are Gautam, Manoj and Kaushik. And the team name is MATS from Shastra Deemed University, Shasta Rajan, Raghav and Balaji. And the registrations that we got from all over the country. We even got from premium IITs also. And yeah, so these are the creamy people that came out of this. And over to you, SSN Mosphere. I'll play the video at last. They will have their own small videos. I'll play the event that happened for 2 nights. That's nearly 48 hours. I'll play that. Yeah. I'll take the
Yeah, hello everyone. My name is Vinit Roshan Premanan, and this is my teammates Sriram and Ajitesh, and we're Team Mosphere. So we did the robotic arm track, and our proposal is a vacuum sorter. So, next slide. So this all started when we were at VLSID 2025, and we saw Lavina's ma'am's post about the hackathon, and we were like, okay, we definitely need to attend this. It's a RISC-V, it's a hardware hackathon, and it's 48 hours. We definitely need to do this. So our problem statement has 2 major components: picking up the ball and also sorting it by color. And also we had to take in consideration the number of joints of a robot and also firmware size. So with all of this considered, we started the design process. So let's talk about the ball collecting mechanism first. So of course there's a traditional gripper. You've all seen this before. You know, this is just a standard gripper. We wanted to think outside of the box. So we went to inspiration that we saw in real life from, dirt diggers, claw machines, and even application-specific stuff like the ones you see on the right. So, and then after that, we refined our ideas a bit more. So this is just an idea we had for a normal claw machine. This was a scooper idea, and this was one we were really interested in. Just scoop up the ball and also collect it and have the color sensor right there so that we could detect the color while we're in transportation and save time. We also had an XY plane plan for this, but then we realized if the collection bin was not a square and it was a different size, and it just wouldn't work that well because we would have to maneuver it a bit more, have a bit more sensors that increases our firmware size and sensors amount as well. So it wouldn't be as widely applicable. And then, you might have this experience while just vacuuming the house. You'll just randomly pick up a few objects and be like, that's weird, right? And it was it especially happens when you don't want it to. So we thought, why don't we use a vacuum for picking up our objects? It'll be much more widely applicable and it'll be easier that way. So that's the idea that we went with. So let's get to the color sensing now. So this is a standard TC3200 color sensor, which you would probably have seen, and we have worked with this very well. And we have, we use this sensor a lot, so we know what to do. But at the same time, this is not the sensor that we went with, and we'll get into that. So next slide. Okay. So this is this sensor is the APDS 9960. This solves 2 of our problems. This not only detects color, but it also has a proximity sensor. So with one sensor, we could both measure the distance from our robotic arm to the surface of the collection bin and determine if there's an object there. We'll also know the exact distance, and we'll also be able to collect the ball and sense the color with just one sensor, reducing the complexity of our system overall. So with that in mind, we had some initial plans. So using a suction motor and a solenoid valve, we'll be able to collect the ball using a suction gripper and hold the ball in place while our APDS 9960 sensor detects the color while the arm is still in movement. So this will reduce time of sorting as well. And as you can see, this is how we're going to measure the distance from our sensor to the surface to determine if there's a ball, and if so, how to get to it, and use suction to get it. And this is a basic design of our arm. And so we also got into designing a PCB, a custom PCB, because we wanted our product to be clean and look nice, and also not be very messy, so that's easy to debug as well. We also added servo motor testers here to easily help facilitate our testing process. And this is our final 3D design. With both this and the PCB, we worked day and night to get it done on time, because we had to get it fabricated and shipped for the 48-hour hackathon. As you can see, me and my teammates, we worked not only in our homes, but also during class, during break times, and also on bus from our way back from college. So we spend all of our time, day and night, designing this, ensuring that it'll be perfect. So this is our finalized designs over here for the 3D printing files and the PCB.
Hi guys, so as my friend over here, Vineet, told about all those all the objectives which we had to cover. So I'd be covering the hurdles part which we faced during this hackathon. So we got all the 3D designs done on time, but the 3D print failures were something which we weren't expecting at all. So the next slide, please. Yeah, so these kind of failures came in midway, and we also had this particular mechanism for a vacuum thing.
So in order to implement the suction mechanism, we guys refer to what they use in industry. Generally, what are the blocks which comes into play for using the suction and picking up objects. So generally it consists of 3 parts. One is that the vacuum source, usually it's a pump, to create it, and we need a solenoid to contain it and release it whenever we want. And there should be a suction gripper of this sort. We went through the specifications, but with the given amount of time, we could not exactly locate objects with those specifications. So we kind of went rogue with going to refrigeration shops and getting water solenoids they had, going to RO purifier shops, getting water they had, and even we some parts we even found it in our homes and found it in our toolkits, and we kind of tried something towards then it kind of worked, which we'll also show.
Yeah, so 3D print is one issue which we faced. In addition to that, we already gave our PCB to the vendor, and we got it only after the hackathon ended. So that was another thing. And yeah, we had 3 systems with us. One system luckily worked fine. One of our systems had a major issue in the installation part, and the other system completely bailed on us right before the hackathon started. So, and yeah, this is what we essentially did. So I told, right, one system completely bailed on us. That was my friend Vineet's system. So what he did was he brought in his Steam Deck, and we started running Vivado over there. And then, yeah, some of our 3D prints were missing. So we had to get those missing parts also printed on the spot. Thanks to Gopinathan sir also for facilitating that. Next slide. And would you like to cover?
Yeah, so finally, somehow we managed to build this thing which you would have seen here. Before this, you would have seen just the simulations or CAD files of how it looked. We wanted to bring it as close as we designed. So this is what we ended up with. So yeah, and we have a simple implementation. So as soon as we figured out how we could interface our servos, we were like overjoyed that we made our bot to do kind of a cobra or robotic dance there. I don't know if it looks like a dance, but this actually helped us to see how good our servers are, like how responsive they are. Yeah, so I think audio is a bit mixed. Yeah, on. Yeah, and we told like for the vacuum suction tube, we came up with something, right? So we actually had like a suction, cup or something in one of our screwdriver kits, which we saw later on. And we thought, okay, we did an Indian jugaad here, so we took that out. We put a hole through it, and we very carefully we inserted the pumps tube through that, and we were voila, and it worked. You can see here, it's picking it up. So we still, can work on this, but we just had like 40 hours, and we were, this one, hardware hackathons mainly, since we have to run here and there, get things up, it was even more tiring. So 40 hours with very less sleep, we were doing all these things. So, yeah, and here is the final, just the picking, like the motion of how our bot just basically picks the ball. Yes. Yeah. Yeah, you can see that it's pinging the balls right there.
Yeah, just to cover a few points. So as we said, we couldn't get the solenoid valve in, right, in time. So the suction cup here is just working based on the air pump itself. So it doesn't have enough power without the solenoid to pick up the ball as well. So we have to be a bit more accurate in these demos, but in the case of actually having the solenoid, it won't be a problem at all. We don't need to be this precise at all. We just need to hover over it approximately, and the pump and the vacuum mechanism will do the rest of the job. Yeah, and this is our another version of the demo. That one was more up close, so you could just see from a bird's eye view how it looks overall. You will just see it right now. So it's very quick. We just need to be a little bit more precise right now, and that's an issue that can be easily solved. We just need one component to show up. And just we want to finally wrap up by, talking about the help that we had. As Sir said, this was a 48-hour hackathon, right? And while we were provided with sessions about, how to install the SDKs, we were also left a little bit on our own to explore. And at first, while that was a bit challenging for us, we really did have issues with installing the SDK a little bit. And even with that, we had challenges. The mentors that we had and Sir himself were very helpful, and they guided us through the process, and it was a really good process. Since we were only given limited resources, but just enough to learn, when stuff did work, we were really happy. And not only the SDK, but even the interfacing diagrams and documentation were really helpful. And if for something as simple as, let's say PWM, on the video, the documentation was excellent, and we have never seen such control over just PWM in general. Even when we've implemented in Arduino or even in Verilog, right? The amount of customization that we have with the Shakti SoC is amazing. And it was challenging to get it working, but when we did get it work, we wanted to jump and dance and joy, and that's why we did this demo of which we showed you before, right? That was our inspiration. Although it was really challenging, the actual 48 hours were one of the best 48 hours I've ever had. And the sleep afterward was also nice, but this was a really good experience, and thank you so much to the team and Sir himself, yeah.
And hopefully you picked on his accent.
Thank you guys, thank you so much. I think you really appreciate the effort, right? See, the only one difference between the existing hackathons on such kinds are most of them could be done on an Arduino, right, with the existing plug and play libraries. But this one kind is you need to know everything. What is happening inside, just plugging a library, you don't know. It's like a black, a black spot, nothing, it is not visible to you. Here, you need to burn your fingers and learn. And one feedback that we got after this hackathon is conducted, and what we got from the participants was, they said, sir, you should have at least given us a workshop and what peripherals could be used for what, as well as how you should have given some introduction about SDKs. I said, what I said was, we did it purposefully. The thing is, once you don't know something, and if you want us to teach you and let you know, that is very less. Once you burn your fingers and do it there and learn, that stays with you long. That is what they have experienced. And we'll go to the next team. They are from Bannari Amman, BITS Coimbatore. These people are, they were on the maze problem statement. I owe to them. Let me think, what should I tell after them?
So good afternoon to everyone. Okay, we are on a problem statement to build a maze solver robot using the Shakti SoC on FPGA. Okay, generally everyone know how to build a maze solver robot, and then what a maze solver robot do? Like the maze solver is the simple robot which can navigate the path with avoiding the obstructs in the path. Like if a stone comes in the path, means like just only if the problem statement is to don't touching the wall, it will move on the path only. Not touching the walls. Like everyone literally build a maze solver robot in our projects. The main problem statement in the problem is that we have to build that robot using the Shakti SoC. Okay, everyone have worked in the FPGA boards. Like okay, here what we doing is not only using the FPGA board, we also in that FPGA board we have to interfere the Shakti SoC. Like they have a C-class processor architecture. We have to initialize the FPGA into a microcontroller, like not using the FPGA. We have changing the FPGA into a microcontroller, which have been built by the Shakti. So after initializing the setup to microcontroller, then we have to code in that. Like everyone in the Arduino, we have every library available. Okay, then maximally all microcontroller have the library available. Like but in this, we have to only build our libraries. Predefined libraries, then we have to only code like step by step. Initially, nothing is present there. Okay, if we are using an ultrasonic sensor, means there is nothing. Simply two or things only present. Then we have to declare every library. Then we have to check in that library. We have to debug that library. Like we have to done everything by ourselves only. No libraries are present over there. Okay, after initializing this setup, we have to build a robot. Basically, everyone only worked in the microcontroller. This FPGA board is too new to us. After coming here itself, we know everything about that. Before coming, we don't know anything about this. Okay, we just set up how to set up, and we saw some YouTube videos. Then we will come here. Then I will know how to do this. Like initially, we have 0. After coming, we have done something like we have fully hands-on experience, 40 hours of hands-on training. Okay, I'll hand over the tools and integration to Kaushik.
Good afternoon. I am Kaushik from Bannari Amman Institute. Once we got the FPGA board, we are asked to get output on hello world. So we just printed hello world at first. So after doing that, we just used GPI of peripherals for our entire project. So we checked on the example files that they gave and figured out how they declared and how they used the GPIOs. So when we figured out this, and we just give the code for a motor driver and tested the motor. After that, we need to code for ultrasonic sensor. So we just had a code that can enable and disable the pin. So we need to use time to get the distance of ultrasonic sensor. Since it's a sound wave, sending sound waves, we need to enable the trigger pin and need to check when is the echo pin is switching on, and the time gap is calculated, and using that we calculate the distance. So that's the real challenge here. We don't know how to use time here, time in this FPGA. After figuring out that, opening all the header files, we figured out that platform.h had something called m-time. So we used that and calculated the difference in time, and then we figured out how to get the distance, and slightly manually we calibrated how to get calibrated to get the distance. Actually, it threw some other value, and we manually kept the scale and calibrated to what we want. And after that, we already did maze solver using PID controller, actually, STM32. But here we want to make it simple and make it less complex. So we used here bang controller, which just turns on and off the motor, judging the distance. And then, yeah, we actually got the output. Yeah, I'm handing over the mic to Manoj.
Good afternoon all. Here I am to tell the problems what we are facing during the hackathons. The major problem was we are new to the FPGA. We faced a problem. First, we have done the maze solver robot, and we have won some of the competition. But here the issues we faced was on that competition we have used the TOF sensors, but here we didn't find the library for the particular sensors. So we start to look into the sensors and the libraries what are available for this architecture. We look into the sensor, but during the short duration of time we can't able to go through it. So we started to use the ultrasonic sensor. In ultrasonic sensor we used the common trigger pin for all those pins, and echo is the receiver pin. We use echo and get the output based on the time duration of echo and trigger. We get the output from the ultrasonic sensor. This is the common, but we have faced some of the struggles in the FPGA because it is new to us. Then next to it, we are starting to move into a motor driver. In motor driver, we faced issues was, last time we used FNG motor driver, but here we are using the L298 due to the PWM. We tried for the PWM, but due to some of the errors and issues, we started with the GPO pins, and we completed the motor driver and we get the output. Next we started to, some of the issues, what others we have faced are, while moving, there is a we need to align it a PID. It is used to align the maze in the center. But another struggle we faced is, here we can't able to do it in a short period of time. So we started using the Big Bang algorithm, Big Bang coder algorithm. So with the help of that algorithm, it is started to move. It explore the maze and it will solve the maze as soon as possible. Here the outcomes of what we have learned from here. Due to in this hackathon, we have a hands-on experiences how to work on the FPGAs, what are the things we can do with FPGA, and we have done a live product using this FPGA. And here, due to the less availability of library files, we are start to think more about the library files, what are the things. We started to think about the library, other possibility of libraries, what are the things we can do with the available libraries, all those things we are looking into it. This algorithm teaches a lot in troubleshooting and debugging due to the less availability and doing the something what we need to. This is the thing engineering. With the availability, the thing what we are doing is our need. With the less requirement is the engineering up to me. So we have done it with this hackathon. This hackathon teaches how to do it with the less available, with the requirement what we had. And we have also experienced in some of the terminals and softwares, SDK and GDP and Vivado. Vivado we have used here after coming into it. That's all, thank you. Next we are looking into, this is our overall developed a prototype. We are using the ultrasonic sensor and placing the FPGA board. It is the board. We have one of the working prototype video also. It is a sample video. Here the board work based on the sensor reading from the ultrasonic. It will configure based on the trigger and echo timing. It will explore this is a sample mesh given to us. It will explore throughout this mesh and it solve it. Due to the board size and some of the constraint, it is stuck into that. That is the major issues we faced in this. Yeah, this is the sample video. The final video will be shown by the webinar, sir. Thank you.
Awesome. So this one is a sample maze that we gave them. There is one bigger maze that is in 3 cross 3 dimension, which I have a video, I'll show it to you. Yeah, this is again, the feedback that we got from this team was like, the use of Arduino and that the ease of using Arduino was totally destroyed after using Shakti. Like they learnt a lot. What Arduino happens inside Arduino, they were able to grasp everything in using this. The only biggest constraint in this challenge is the board that you see, because the board itself is around 13 inch, I think. So, they need to align the board accordingly so that it doesn't hit the wall. For the turning, they need to see. And one among the team of like the top 13 finalists, one team were able to keep the board in a different alignment. Like I missed the point. I missed the photo of that. They kept the board like this slanting. It is not like they kept it like this. These teams kept it like this. One team just kept it like this, which was a very intelligent move. All these things, they planned it. We gave the constraints very well before, and they did this. And yeah, they were also able to crack the maze a little bit, but they were facing struggles. So that's why they were not able to come into the top finalist. But the idea was awesome. The keeping the board in a slanting way where they can easily gaze through the maze. Yeah, next team is from Shastra. Welcome them.
So good morning. We are teammates from Shastra University, myself Raghav, and my teammates Rajan and Balaji. So we competed in the maze solving track of the Shakti FPGA hackathon. And our task was to create an autonomous rover which can navigate through the maze using the real-time sensors, motor drivers, and the path planning algorithms. So the solution proposed base was we designed a chassis to perfectly fit the Nexus video board. And for navigation, we used GPIOs and PWM for controlling the motor precisely. And we used GPIOs for IR sensors to detect the walls. And also we used I2C to get the readings from IMU for the precise turning and etc. And we used a wall following algorithm, like there is the left wall following algorithm for the path finding. Next. And in previous slide, we spoke about the peripherals. So in the FPGA board, we have dumped the Shakti MCS file to configure it as a microcontroller. And we use the OpenOCD and GNU debugger to compile and run the programs.
Hello everyone, I am Balaji. Okay, so we used the Nexus FPGA board and IR sensors, N20 motors and wheels. We used lithium-ion batteries for powering it. We used MPU 6050 as the IMU. Okay, and then we used L298N motor driver. Okay, so this is our prototype. Previous slide. Okay, can you see here? Okay, so you can see two chases here. Okay, it's a little bit blurred. Okay, so that's the bottom one, and then the square is for the top. So we'll be fitting the board on top of it. So this was our prototype initially. We made some changes to it later. So this is how it turned out to be. We used some bad grip, cricket bad grip on the tires to improve better friction because the wheels were slipping. Okay, so we faced some challenges. Okay, so as Sir mentioned before, for us, the gears in our N20 motors got stuck. We luckily had a spare, and we used that and we also had to use PWM to make sure that both of the motors runs in the same speed. Also, we used IR sensors for calibration. So we have to make sure that the reading that we are getting were very correct, and so we had to also get the data from 3 IR sensors at the same time and also run the bot simultaneously. And we had a power bank to power the FPGA board, but we were then later given a lithium-ion battery. So with the increased weight also, it was a little bit of a challenge for us. And then, okay. So for the last point, yeah. So on the software challenges, we had to code in C and then dump it onto it. It was a little bit tricky for us, and that's it. So for future improvements, we did a normal maze algorithm. So we can make an algorithm for complex mazes, that mazes which have more than one path to the destination. So it will choose which is the best one and then use that. And then we can have a better algorithm in which it doesn't get around in loops in the maze. We can make that. And we used the IMU to make sure that the turns that it made was exactly 90 degrees and that it moves more precise. And we can also implement ML in adaptive navigation.
So the key takeaways for us is that we understood the Shakti SoC architecture and we gained hands-on experience in integrating them in our rover. And we understood the memory maps of the peripherals which are connected with the SoC such that we were able to access and control the motors and sensors. And we also developed and tested bare metal applications. We didn't use any libraries which was available. We didn't use the version 2 of the SoC. We used V1 and we developed and tested the bare metal applications through the Shakti SDK and tools. Yeah, so that's it. Thank you Shakti teams and Chakra Innovations for conducting this hackathon. Yes, sir. And I'd also like to thank my mentor, Dr. R. Shivaraman sir and N.S. Manigandan sir, Shastra University. Yes. Thanks.
Great. We have a 2 minutes video of the entire 48-hour that hackathon happened. Just give me some time. The final part of the video, the music was missing because the video was edited just before getting inside the stairs. So that was the thing. Any questions? Team, come. Any questions? Any questions? Okay, let me start here. Thanks.
Okay, thank you very much. Again, the same in-house announcements. So we have like 6 counters. So please feel free to spread out and then have lunch. And then if you have some time, please also please visit the stalls that we have in the 6th floor. And see you by 2:10. The participants are returning from the lunch. Meanwhile, I take this opportunity to welcome Professor Kamakoti, the Director of IIT Madras, who has joined this session. Sir, we have a short video for you. Probably you would have surprised like how the workshop had went yesterday, sir.
Hello everyone. We'll now have a talk from the Vice President of Technology, RISC-V International, Andrea Gallo. Andrea heads up the technical activities at RISC-V International with a mission to facilitate the technical vision, cultivate stakeholder engagement, and drive the strategy in a deeply engaged collaboration with RISC-V members across work groups and committees, and growing the adoption of the RISC-V instruction set architecture. Prior to RISC-V International, Andrea had held multiple roles at Linaro, starting all ARM data center engineering activities ground up from firmware to complex cloud workloads. Later, as the VP of segment groups, he oversaw verticals from IoT to HPC, including smartphones and AI/ML. In his last years at Linaro, he served as Executive VP of Business Development, managing all membership contracts and starting new collaborative projects from automotive to Windows on ARM. Prior to Linaro, Andrea was fellow at ST Ericsson for smartphones and application processors and served as the first member representative in the Linaro TSC. Over the years at ST Microelectronics, he consistently led the optimization of hardware-software architectures for new ICs and set up remote teams in India. Andrea holds a university degree in telecommunications and speaks fluent French and English, in addition to his native Italian. We'll now listen to the recorded presentation from Andrea.
I'm Andrea Gallo, Vice President of Technology at RISC-V. I'm honored to be today with you virtually for the second Digital India RISC-V Symposium. RISC-V is the industry standard ISA that expands opportunity. Global standards are catalysts to accelerate technical innovation. Some of the examples of standards adopted and implemented every day in our life are USB or the World Wide Web. So standards are specifications that everyone can access freely and can use and refer to and comply to develop innovative products. So USB is a standard, and then your USB devices are implementations of the standard. Similarly, RISC-V is industry standard instruction set architecture. So all together, collaboratively, we join forces, all the companies that want to progress and advance the RISC-V ISA, we work together to curate the RISC-V ISA, to develop new extensions, improve functionality, improve performance, improve security, all together. So RISC-V is the place where we evolve the ISA, also collaborating all together and applying a very rigorous specification development process. Then every member can freely develop their own RISC-V implementation. Today, RISC-V counts up to more than 4,600 members across 70 countries. Some are academia, some are individuals, many are commercial and very successful companies. Some design IPs, some design chips, and some design end products. It's a very lively ecosystem. We are measured by our technical contributions. We're not measured by revenue or any other financial KPIs. We're measured by contribution to the technical standards. And so last year in 2024, we ratified 25 new technical specifications, and we currently have more than 70 working groups where members like you in this room collaborate together. Let's look at the market potential first. RISC-V has an incredible potential. The SHD group estimates that in 2031, RISC-V cores and SOCs will surpass 25% of the market and will count up to 20 billion units of SOCs. Some SOCs will include one RISC-V core, some SOCs will include 4, 10, 20 cores. So we are counting SOCs, we're not counting cores sheet anymore. And so the preview from the analyst is that we will grow from 2 billion SOCs in 2024 up to more than 20 billion SOCs with multiple RISC-V cores in 2031. This is a preview of the 2025 report that is going to be published soon by the SHD group. The same report forecasts the market share of RISC-V in 2031 in all segments, from consumer to automotive, from computer to networking, industrial, data center. So the market share to be between 25 and up to 40%, depending on the specific industry vertical. So RISC-V is the technical foundation for lasting success. Countries and governments invest in RISC-V because they need to drive their digital and technical sovereignty for their countries. They need to accelerate local innovation. They need to create pools of talents and competence in their countries. So they are incubating technology ecosystems that will move from academia and research to commercial products and industry. And thanks to RISC-V, governments and countries are investing locally in their countries, but are accessing a global worldwide market and collaboration. Multinational companies are investing in RISC-V. They need to control their destiny. They need to control their strategic roadmap. They need to build new opportunities for innovation. And of course, they also need to avoid vendor lock-in. They need to avoid situations where suppliers can change the rules of the game overnight. Researchers and academia, of course, leverage RISC-V to build their talents of students and PhDs and startups. And RISC-V was born in academia. And RISC-V Thanks to the energy and innovation from academia, RISC-V moved into real commercial products. And this is what we see happen every day. And being part of the RISC-V ecosystem allows universities, academia to be part of a global network of research. And startups, of course, are investing in RISC-V because they can immediately focus on their value add. They can develop new innovative products straight away, and thanks to the collaboration with all the RISC-V partners. A very important aspect of RISC-V is collaboration, and our RISC-V summits are a key ingredient. We are very supportive of RISC-V days and workshops and symposium worldwide, and we are very supportive of this initiative today. Last year, we had the 3 major RISC-V summits in Europe in June 2024, in China, and then in October we had the RISC-V Summit North America in Santa Clara. And we had an incredible participation both in person and remotely. And we're very supportive of the digital India RISC-V Symposium today, of course. Another way to engage and be part of the RISC-V ecosystem is, of course, to learn and grow your expertise. And as such, RISC-V offers a full set of free online courses that everyone can benefit from. You can see the full list from our website. The courses range from software to hardware, from developing applications with a real-time OS to Linux device drivers, but also designing a RISC-V CPU core. That's my favorite course. I really encourage every student to attend the course. What is happening, what is accelerating innovation, is that, if you think about it, we are moving from old traditional SOC design to a workload design silicon. What is happening with RISC-V is that you analyze workloads, you identify performance bottlenecks with existing technologies, you identify the critical points in your workloads, in your target applications, and then you can use RISC-V to design new extensions, new instructions for your custom workloads, or new architectures made of multiple RISC-V cores, and in the end, you design silicons that are optimized for your workload. So we are entering the area of workload design silicon. This is the major disruption that RISC-V is enabling. And so I was mentioning the ISA, the instruction set architecture, and I was mentioning designing new instructions and the work that we carry on all together in the RISC-V ecosystem. So the way it works is that we have a base core instruction set architecture, a very limited and very efficient number of instructions. And then we have a modular set of additional extensions that can be added to your overall specification for your design. Extensions range from floating point, bit manipulation, vector, matrix in the future, security extensions, hypervisor and virtualization, domain isolation, crypto. And there are also non-ISA extensions that we all together standardize in terms of interfaces and specifications, and they cover interrupt controllers, timers, IOMMU. We also specify software and hardware interfaces, and in particular the boot and runtime services. So the concept of profiles is that we specify a certain set of mandatory extensions that are required for RISC-V processors in a specific segment. And in particular, right now, we have the application processor, the embedded processor, and the microcontroller. So RVA, RVB, and RVM. We specify common peripherals, common hardware and software interfaces for industry verticals like server, which is ongoing, mobile, automotive, or embedded edge AI. And once we enable all these, then we can easily port enterprise-grade operating systems like those from Red Hat or Canonical or SUSE, or mobile like Android, or automotive, or Yocto as embedded, or Zephyr, FreeRTOS, and other RTOS for microcontroller packets. RBA23 is an important profile that we ratified last year. The key mandatory extensions that shall be included in every RBA23 compliant processor are vector and hypervisor. So these are extensions that set the bar high enough to have high-performing modern application processors, and they ensure binary compatibility. So when the operating system vendors build their operating systems for the RBA23 profile, then their binary distributions will run seamlessly on all the application processes that comply with the RBA23 profile. I was mentioning last year we ratified 25 specifications, so we have a list, and we sorted the list in terms of major buckets. So some extensions improve performance or add new formats like the BF16 that is very important for machine learning. Another set of specifications targets security and resilience. Specifications like pointer masking, landing paths, shadow stack, these are critical to ensure that the execution of our software does not get compromised by cybersecurity attacks. For this year, 2025, we are focusing on ratifying the intrinsics for vector, so that math libraries can easily leverage the vector extensions. And we are also progressing on the matrix extensions that are very important for AI and for high-performance compute. And the other important target for 2025 is the ratification of the server platform. Hardware alone is not enough. You need software, and RISC-V has been focusing a lot on enabling the software ecosystem. We ship the latest development boards to the key open source project maintainers. We have the landscape.risc5.org page, where you can see all the projects that we have been enabling. And we are working very closely on software porting and optimization with the RISC-V software ecosystem, the RISE project, and our colleagues and friends at RISE identify key workloads, key components, key frameworks and projects that need to be ported and optimized for RISC-V. When you leverage the RISC-V ISA, the RISC-V collaborative model, the RISC-V innovation from the entire ecosystem, from all the partners, then you have an incredible starting point to add your own innovation and build new disrupting products. And this is where we see exactly the initiatives in India with the Shakti processor. It's something that we very highly support, and we think that is the right way to go. So we're very happy for this event, the Symposium today, and we wish you a great event, a great conference. And we would like to leave you also with the link to the next RISC-V Summit in Europe in May in Paris, France. We're looking forward to meeting you all in person. Thank you for having me.
Good afternoon. Our next speaker is Sharat Kaul on DIR-V. Sharat Kaul is OSAT consultant with Keynes Semicon, Bangalore, India, and comes with over 30 years of semiconductor design, manufacturing, and embedded systems experience spread across the globe with companies like Texas Instruments, Dallas, and Synopsys, India. After 10 years with Synopsys, Sharat established his own solar energy startup, Solar Apps Energy Private Limited, providing rooftop solar solutions. Prior to joining L-Phones, Sharat had set up Krypton Solutions, an electronic manufacturing services, where he currently serves as Executive Director, followed by the Indian Electronics and Semiconductor Association as VP of Strategy, Innovation, and Execution. Sharat completed his BSc from Bangalore University, the BSEE from the University of Texas at Dallas, and MBA from the Cox School of Business, Southern Methodist University at Dallas, Texas. At Keynes Semicon, Sharat is responsible for the strategic roadmap as well as packaging capacity building, business development, and R&D commercialization. Over to Sharat.
Thank you so much. Good afternoon, everybody. How is everyone? So, just by a quick show of hands, how many are from outside of Tamil Nadu? Wow, that's fabulous. That's around 50%. Okay. And I also like to ask one poll question also. How many here own a Samsung phone? Golly, that's about 40%. How many here own Apple iPhone? Okay, around the same. Come on, up hands, I need to see iPhone. And how many own an Indian phone? Come on, let me see. Yeah, usually wherever I go in the country, it's usually 1%, 1 out of 100 or 1 out of 200. Okay, so that's the reason why we're here. So thank you, Professor Kamakoti. Thank you, team from IIT Madras. Thank you, Lavanya. Thank you, Rise Labs. You all are absolutely fantastic. The work that's going on with Shakti Core is outstanding. To see this audience here is absolutely thrilling. You're all the future. The country depends on you, is counting on you to make it happen. There's no more chalta hai attitude. There's no Indian Standard Time anymore. Those days are gone. We have to work fast, otherwise we're going to be left behind again. And this is the time to grasp it, okay? So I just wanted to talk a little bit about industry involvement in DIR-V. Most of this is academia and the hackathons and etc. But Professor Kama sir had asked me to help organize the industry around RISC-V, and that's what I've been doing since November 23 when I spoke here last. RISC-V was basically christened or named on 27th of April by Sri Rajiv Chandrasekhar ji, and basically is NSM 2.0. NSM is the National Supercomputing Mission, second version, and in the NSM 2.0, there's an area carved out for RISC-V and the RISC-V Knowledge Center, and then CDAC Trivandrum and Mr. Krishna Kumar Rao, and the work that they're doing there is another part of NSM 2.0 for IoT applications, and then we also have the NSM 2.0 for high-performance computing, which is done in collaboration with CDAC Pune and CDAC Hyderabad. So this is NSM, and DIR-V is Digital India RISC-V, which is a part of the NSM program. It's not an entity, but it's just a name. And the idea was to see partnerships with startups, academia, the global majors. Of course, we're a part of RISC-V International, and I'm going to talk a little bit about RISC-V International and how India plays a role in that. And of course, this is overseen by the Ministry of Electronics and IT. CDAC falls under MEIT, NILIT falls under MEIT, SCL falls under MEIT. And there's a tremendous opportunity, obviously, with CDOT and railways also, and all of it can be used, RISC-V can be used for all of these, which I'll talk about. So I'll just spend a little bit of time, forgive me for the formatting, and it's a little bit old, I haven't updated it, but what I want to emphasize here is where we are in the country today. And on the x-axis, what we have is clock frequency, and on the y-axis, what we have is technology node. Does everyone know what technology node is? When I say 180 nanometers, does everyone know what that is? Good, 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 good. And everyone knows clock frequency. So basically what we're doing is, what I tried to do was plot the Indian companies and Indian RISC-V cores to a large extent on this axis. And from 0 to 100 megahertz, there's a range of applications, low-end applications like motor drives, toys, and white goods like microwave oven, and you know as very well that these white goods are getting smarter and smarter. They're having touchscreen displays, they're having human-machine interfaces. Then as you start moving up on the x-axis to higher frequency ranges, you start getting into the IoT applications that were shown in the hackathon, like robotics, like drones, forklift, smart meters. Then you progress further up the x-axis to higher frequencies above 1 gigahertz, and you start getting into the telecom range. So the C-dot, the 4G, 2.5G, 4G, 5G, base stations, smartwatches, laptops operate, as you know, about 1 gigahertz and above. Then there's single core, there's dual core, et cetera, et cetera. And then we're starting to look at even higher end and greater than 1.5 to 2 gigahertz. And we start getting into artificial intelligence, data servers, facial recognition, all the stuff we were talking about, convolution, I beg your pardon, the matrix multiplication, convolution, et cetera. So on the y-axis, if you see, we have basically 2 clusters. One of them is focused around India's one and only fab, which is, can anyone tell me which is India's fab? Yeah, good, everyone knows. And does everyone know what technology node SCL is? Good, everybody knows. So we obviously have taped out Shakti at 180 nanometer, we've taped out Vega at 180, and more work is going on with Kunal, who you met yesterday, building the open source flow there. And we also have a cluster, Shakti was also taped out at Sintera at, I think that was 110 if I'm not mistaken. And then a large bulk of the new startups that have come and emerged, like Morphing Machines, Mindgrove, and Caligo Technologies that you see has been taped out at TSMC 28 nanometers. This is basically it, and more is coming down the road. Ahisa is also on that list, which is coming out with their Vega core derivative for GPON, for fiber optics. So this has to change, and then also you can see that from 0 to 1, around 1 gigahertz, you have the E class, the middle of the pack is the C class, and the I class. Now, why do I bring that up? Is because I want to draw a comparison. Everyone knows that for the last 50, 60 years, there's been predominantly 2 major architectures. These are x86, right, which is Intel and AMD, and then of course ARM, which is RISC. And as you know, ARM was predominantly for wireless applications and low power, whereas x86 is what is today also driving the data centers and the laptops. But now we're starting to see that the RISC is starting to be used in high performance computing as well. Now, the next question is, what does that mean for RISC-V? What does that mean for DIR-V? So this is an example from the ARM website, and it just gives you an idea. Now, you might ask yourself, oh, I have a RISC-V core, I'm all set to go. That's not exactly true. We have to create architecture-specific RISC-V cores using the Indian instruction set. Just look at this table. Within ARM itself, you have A class, so many architectures, R class, so many, M class. You have Mali, which is the GPU. You have something called physical IP, the memories, single port, dual port, DRAMs, SRAMs, NAND, built-in test. There's so many. Let me tell you, the opportunity here is immense. And unless we start building architecture-specific RISC-Vs, we will not be able to keep up. Let me tell you that each and every one of these could potentially be a startup. Artisan got bought. Viraj Memories, they got bought. These were all startups. And this is what is going to be needed in order for us to make an impact with RISC-V. We have to be building RISC-V architectures for IoT applications, like I mentioned in the previous graph. RISC-V architectures for the middle segment, the E class, and then the C class. So please remember that the work does not stop just because we have a Vega, not just, but when we have a Vega or Shakti, we have to build architectures based on the Indian instruction set. So a lot of support has been going on in the country. MAIT has announced a scheme of many programs. As far as the academia goes, we have the C2S program. Has everyone heard of the C2S program? Good, good, good. C2S program allows you to have the EDA tools. Then we have what's called the DLI program, which is the Design Linked Incentive. And C2S is for academia, DLI is for the industry. And what that basically does is it gives you access to the EDA tools, and then it actually gives you access to what's called MPW. So once you do the design, the front-end design to synthesis, back-end design through physical design, LVS, DRC, you send the JDS2 to the wafer fab. Then you have to get the wafer. You have to probe it. After probing it, you have to package it. You have to test it again with the same tester. Then you have to put it on a board, and you have to test it again, and then it goes into the end system. This is what's called the chip-in program from CDAC. So what it enables you to do is go from the academic R&D POC approach. There's a platform for you as an entrepreneur and a startup to actually get your design to silicon, and your silicon onto boards, and your boards in turn running real-world products, which I showed. This is all available for you today. In my humble opinion, the government has done their job. The funding is there. The government gives 50% funding from the center and 25% funding from the state. Plus, you get the discounted EDA tools, plus you get the discounted IP. With these components, you are able to get your idea to realization. So I'll talk a little bit and wrap up my presentation about RISC-V. You would have heard the presentation today. RISC-V International, again, is a global effort, and they have 3 categories of membership: Premier, Strategic, and Community. Premier membership is 2 crores, and there's around 25 of them the last time I checked. Out of these 25 Premier members, 13 of them are from China. And as of today, in fact, MAIT is no longer a Premier member. We have 0. Now, what does that mean for India? RISC-V International creates the committees, the guidelines, and the specs for RISC-V globally. We are nowhere on the picture, hardly. Lavanya is part of one of the committees, and Neil Gala. 2 people in the country are on these committees, and there's hundreds of committees. This is unacceptable. We need more participation from the academia, from the industry on these committees. Strategic member is $2,000 for less than, this is for companies, for $2,000 for less than 10 people and $5,000 for more than 10. I find that also a little bit prohibitively expensive, but we do have about 8 to 10 companies which are strategic members. Now, what does that mean? The premier members, I believe, get 5 votes. The strategic members get 2 votes, and the community members get 1 vote. Community membership is free of cost. Each and every one of you are now ambassadors for your colleges. We have conducted roadshows leading up to this DIR-V Symposium in Gandhinagar, in Andhra Pradesh, in Jammu, and in Bhubaneswar. At each and every one of these locations, the halls were at capacity, and we had representation from universities, not just the IITs, but around the IITs, we had participations from 10 to 15 engineering colleges. And my call to action to them, and my call to action to all of you is be the ambassador for RISC-V. Go back to your college and register as a community member on RISC-V International page. I want to see your college logos on that page. It's free of cost, and it gives us a vote. We may not be able to get strategic membership, we may not be able to get premier membership, but one thing India has is lots of people and big numbers. If we can build a community of community membership, then maybe we can move the needle in terms of DIR-V with RISC-V International and get our specifications on these committees. So we have Manipal, Nirma, of course IIT Madras is a leader, Kakatiya, Deccan, CDAC, SAFL, etc., but we need much, much more. I want to see 2,000 universities signed up on the community membership. I want to see 2,000 votes from there. And what we've also done is the industry we have a WhatsApp group, and now we have around 80 members representing about 50 companies, which are all working with RISC-V. We have a DIR-V Academia WhatsApp group also, where we have around 20 universities. That number has to grow. Further, we've created a DIR-V GitHub repository. Okay, RISC-V International and the entire RISC-V community are all on GitHub. We're creating an academia GitHub repository and a industry GitHub. In the academia, we're breaking it out into 4 zones, north, east, southwest, with the IITs taking the leadership role, but all of your colleges and you must get your Linux accounts and have a GitHub repository. Now, what does that mean? That means we can collaborate. That means that when you're running your code, when you run into failures, that you can collaborate globally. The main thing about RISC-V and DIR-V is, as a country, we should speak as one voice. We should all be, if we all speak as one voice, our voice will be heard and our voice will have its impact. One voice, we don't work in silos, and we bring the entire country together under one umbrella. And that RISC-V Knowledge Center is going to be IIT Madras. So I hope that's clear. Does everyone, is it very clear what your call to action is? What? Are you going to go back and put your logo on the RISC-V International community site? Yes or no? Yes. I can't hear you. Yes. Good. So thank you very much. I'll conclude my talk, and I would like to now call my professor, actually. So our IIT Jammu Roadshow would not have been possible without the help of Dr. Siddharth Maheshwari. He is an assistant professor in the Department of Computer Science and Engineering at IIT Jammu since 2023 June. He completed his B.Tech from IIT Guwahati in 2013 and his PhD from Newcastle University. His interests include hardware-software co-design to mitigate computational and energy bottlenecks of big data applications. He's working towards solving real-world challenges such as improving water quality through molecular diagnostics that includes genome analysis and antimicrobial resistant surveillance. He's also working in the domain of battery management systems and novel battery pack design for Indian tropical climates conditions in order to address challenges in the e-mobility sector. Another vertical in his research interest lies in a novel machine learning algorithm called Setlin machines that is promising candidate for embedded IoT and edge applications that often encounter challenges from the resource and power energy budget constraints. With that, I'll hand it over to Professor Maheshwari. Thank you so much for your time. God bless you, and Jai Hind. Thank you.
So, hello everyone, greetings, and thank you very much for inviting me here. Thanks to the director, IIT Madras, Professor Kamakoti, for this vision of Digital India RISC-V and this DIR Symposium. And thank you the IIT Madras team and Sharath for introducing me, and Kunal, and for organizing Kunal and Arvind, organizing Arun as well, organizing the roadshow. So I am basically here to maybe introduce a very interesting use case of how we can use RISC-V based many core architecture for something called embedded genomics. So how computational genomics and genomics is becoming a big thing in the field of medicine, and it has applications, numerous other applications. So I will just give a small talk on how we are going to use this. So I have multiple research verticals, but mainly over here I will be talking about this molecular diagnostics and the embedded genomics. So just a very small basic introduction to what a genome is. Genome is a complete genetic material of an organism, and it is the genetic code which is required to build, maintain, and clone an organism. It is located inside a nucleus of the cell. And this is like a human cell with multiple chromosomes, but the small bacteria and all, they generally have just one chromosome, and a chromosome is built of a double helix DNA structure, and the entire genetic code is building block is DNA molecules, which is ACGTs basically. So once when we talk about obtaining the DNA sequence, we basically want to obtain a sequence of ACGTs, which are a genetic code of a particular organism. So what is embedded genomics? This is a term which I coined out during my PhD. Basically, first I will set up the motivation why genomics at all. So genomics is being used for diagnosis, prognosis, and treatment of over 7,000 diseases. Almost every disease is an action of protein, which is in turn produced from RNA and then DNA. So ultimately, all treatment diagnosis can be rooted to the genome analysis or genome of a particular organism. And it finds application in medicine, as mentioned, and forensics, agriculture, and many other fields, actually. So the main challenge is, genomics today is one of the largest data contributor. For example, just an estimate to, sequence one human being's genome, we require as much as 230 GB of data. And even though our genome is just 3.3 GB long, gigabases long, we need to produce massive amounts of data due to the current limitations of the sequencing process. But this is the best we can do, and it is extremely important. So the challenge is, how to deal with this massive amounts of data and the associated computational and energy cost. So our aim and objective is to, reduce the overall computational cost. There are two parts of it. First is obtaining the genome from the organism and then processing the genomic data and doing the genome analysis. So right now, this part actually aims at, reducing the computational cost of genomics. With, the computational cost here would mean the hardware requirements, the power requirements, the energy requirements, and the maintenance of those systems. So what we want to do is use hardware software co-design to reduce, all these parameters, optimize all these parameters and move towards net zero genome analysis using embedded genomics. So just a small overview. Basically, we have an original genome, and that is a sequencing machine, Illumina sequencing machine. And we basically break this into smaller pieces, and we use this machine to get a digital form of these subsequences, and then we do a lot of genome analysis based algorithms to actually reassemble the genome and then analyze the data for mutations and all other downstream analysis. So what makes this challenging is, since, even within the same species, there will be a small percentage of difference. For example, among the human beings, we are almost 99.2%, 3% similar, but this is 0.6, 0.7% of difference in such a huge, genome makes things difficult for us to reassemble the genome from the smaller pieces. So we need to bring into, this problem becomes an approximate string matching problem. And also there are sequencing machines, so there is sequencing errors as well. So this makes it very challenging, and we use multiple methods to deal with it. But the whole overall point is that this complicates the issue with the large amount of data, massive amount of data which is available, and then alongside this approximate string matching algorithms make things complex for us. So we have tried, traditionally, you will go for, data centers would go for, complex Intel processors, and they are good, but then you require a lot of things associated with it, maintenance, energy cost, the hardware cost itself. And then there are GPUs as well. There are tremendous amount of literature present where they try to accelerate some part of the algorithm using, data parallelism on GPU and achieve, But what our vision was to, can we do it on a single board computer like Raspberry Pi and Odroid boards, and do the same amount of computation with such large amounts of data involved and bring it down to an embedded board which has less than 4 GB of available data. So we proved it that, ultimately bringing down to the embedded systems level, we can bring down the energy cost of this up to 5x, and the cost of hardware is also almost 10 times less. But this is 2 times slower. So we need to compensate for the computation time. And why it is possible is because we hypothesize that, the genomic computation, looking at the nature of the data, it involves mostly, it actually just involves integer-based arithmetic. And also it is very high, it can be highly parallelized in, the algorithms are can be highly parallelizable because all these small fragments of DNA can arise from anywhere and they need to be matched with each other. So there is no interdependency of data. So using these two hypotheses, we basically, build this, embedded cluster using off-the-shelf embedded boards. That one, the right one is Raspberry Pi cluster, the left one is Odroid N2 cluster, with the aim that, with the same power level and still having almost comparable hardware cost without any cooling requirement and nothing like that, and still we could achieve almost 10x theoretical speed up. So this is something in pipeline, and now since the sequencing technology has evolved with, new types of sequencing technology, 3rd generation, 2nd generation, so we are in the way in IIT Jammu to build a complete unified software solution targeting this hardware to provide a hardware software co-design based solution to computational genomics. So what we want to do with RISC-V is that rather than going for an off-the-shelf board, we want to design our own many-core RISC-V architecture, fine-tune it for these kind of application. The application would be more towards integer arithmetic in a task parallel fashion. But it is not limited to it. Anything which falls in this category. So like Edge AI, and I also work in settling machines, which involves only integer and logic-based arithmetic. So many algorithms, and also when you try to bring down, AI algorithms at the edge level, you ultimately have to give away with the floating point computations. So this particular idea can be very much useful over there as well. So that is the idea of moving forward. So this is provides an overall end-to-end solution for genome analysis. So this lab in a van and lab in a suitcase idea is basically already available in Newcastle University, where I did my postdoc and PhD and working with Professor David Werner. So this is something, the right side, you have almost every equipment where you can go to a river or any water body, you can collect the sample, do this genome sequencing and do this visualization. You actually have everything over there, other than the computation machine. So this is what we want to do. So we want to, we have already started, building this up, and we have already started our experiments in IIT Jammu. The second part is the right-hand side. You see all the types of analysis which we will do with water. So that will involve, conductivity, cation, so chemistry part as well, and then the molecular parts as well. So generally, we never in STP plants or any treatment plants, we never go for checking the microbial diversity of water. We only try to see, what is the oxygen, dissolved oxygen levels, and maybe treat water before we release it. But now this has become a serious challenge because with the rising antimicrobial resistance, the cost of treatment will become, unbearable in coming decades, and also the mortality rates will be significantly high. So the diseases which are, very natural, very common today, and can be treated with antibiotics which you take for 3 days or 5 days as prescribed by your physician. But this is going to become very challenging because now we have almost resistance registered for almost all available antibiotics in this world right now. So we need to do something to monitor and control the rise of antimicrobial resistance. So for this is what we are doing. We want to create a map of what is the current status of antimicrobial resistance in this country. But this requires massive amounts of data to be produced and massive amounts of data to be processed. And this is where we want to. That is why this is a very important challenge which we need to address using our own processors and customized processor design for embedded systems. Thank you very much.
Okay, friends, good evening. Little more? Thank you. So I thought I'll spend some 15-20 minutes because today we are really happy, actually surprised that for a semiconductor event, we are seeing this auditorium full. So let us start with a good round of applause for all of you. I jovially say that even the monkey at IIT Madras wants to do only machine learning. Now we have moved that stage out, and there is enough stress for us to basically look at hardware, semiconductor electronics in a much, much more detailed fashion. Let me start asking some questions to all of you. As a prof, I love asking questions. So, what's the expansion of VLSI? Can you just put your hands up? Whoever wants to do. Okay. So let me take that person here. Yeah, get up. So what's VLSI? Do you think I'll ask that question? Is there any other interpretation for VLSI? Okay. I have this acronym, a very large source of income. And very large sink of income also. Okay, so that also we must keep in mind. The issue here is, friends, today the brain of any computing, the fundamental building block of any computing starts with hardware. If you look at the well-organized compute stack, there is the digital hardware. A careful organization of them brings you to the microarchitecture. Then there is the operating system. Then there are systems, softwares including compilers and other DLLs and other libraries. And on top of it sits the application programming. So the fundamental root of any computing system is hardware, and we need to make that correctly. What's the big challenge in hardware? It's a one-way ticket to the moon. If you have a software, you have a bug in it, what do? Works? If you have a bug in it, what we do? We release a patch. Who finds the bug? The users. Report bug, you go and report it back, right? And then you fix the bug. As a vendor, my release 2.0 is all the bug fixed of version 1.0, the bugs found by you. Correct? So I make money out of bugs. But in the case of hardware, if there is a failure, what can we do? Nothing. A billion transistor hardware, there is some fault inside. We can't go and open it up and do any patch. We have to just go and dump it. So that's the real challenge here. So hardware, friends, it's a one-way ticket to the moon. We have to do it correct. You have to do it correct the first time. Many startups can't even afford a second round of actually manufacturing this. And that is the real challenge. So hats off to many startup companies who have demonstrated today. They have stuck to hardware and said they will make business out of hardware. That requires enormous amount of courage. If some of the startups are here, please do get up. I think we should give a grand round of applause for all of them here. Thank you. Haisa, Incor, others, Mindgrow, Chakra, Vyoma, Securis, all of you. Thank you very much. Thank you very much. Friends, the brain of any electronic system is microprocessor. Microprocessor tells you what the system needs to do. The program written there, if at all you want to make the system behave in a different way, you have to crack the microprocessor. You have to crack the code that executes. So that compute stack, which is in the form of this microprocessor plus the code, it can be a bare metal C code or some real-time operating system or some operating system and some compute stack around that, that need to be compromised today or that need to be changed for the system to behave behave differently. And that is why microprocessor becomes extremely crucial. There are two aspects of security. Two aspects of verifying whether a microprocessor is correct or not. One is whether it does what you want it to do. And that's a very easy thing to do. Because you have certain programs, you know the outputs, you can put it, you can see whether the outputs are generated, you could have automated testing, etc. To find out whether it does what you want it to do is very simple. The other side of the story is it should not do what you don't want it to do. And that's going to be extremely complex. Because you don't know what it doesn't want. This process has to do these things. That is well defined. What it should not do, it's a very large universe set. And we really don't know what is in store inside that black box that could, suddenly burst out at some critical juncture. We have seen pagers bursting, and it could be a trigger that could have come through a microprocessor which has triggered some sensor to burst it. Correct? So, suppose I have a 32-bit instruction length. How many instructions are possible? 2 power 32. How many instructions are there in ISA, RISC-V instruction set? How many instructions are there in the most complex? Intel. Intel is not a 32-bit. Intel goes even 80 bytes, long instructions. Can go from 1 byte to 80 bytes. It's a complex instruction set of computing. So how many instructions are there? Some 10,000, let us say even 10,000. So how much is pending? So there are so many patterns which are undefined, right? And that is precisely which could be used. There could be some pattern unknown to you which can come and break the entire compute stack. And so, if we are really talking about security, if we really want to have complete guarantee about the performance and the functionality of an electronic system, the microprocessor inside that must be indigenous, must be known to you. The source code should be known to you. If you are going to put it on some very critical program, Critical in the sense not strategic. We are not going to wage a war. We are not going to make a nuclear bomb. But, we want to put it on your power sector today. Friends, there was an attack on our power grid. Right? And any attack on such type of SCADA system, first target would be the microprocessor in the SCADA system. Correct? So, if you really want to put it on some very critical infrastructure today, that source code, if it is known, that will give us lot more of confidence. The RTL, the SDL must be known. And that is precisely the genesis of the India microprocessor program. And we started off with Shakti and Vega. And many people are now doing many versions of this RISC-V processor. And we need to keep this momentum going. Friends, today, 100 crore smartphone users are there. And each smartphone has multiple such chips. Many small microcontrollers which do some very interesting activities inside. Handling your camera, handling your many other peripherals. Now, 100 crore chips, 100 crore smartphone users, assuming every 3 years these people replace, yes, whether you want it or not, the software there runs so slow that make you replace it. And so you will have 30 crore per year replacement. And let us say we have to make the arithmetic easy, let us say we have 300 days a year. 65 days goes on Saturdays and Sundays maybe, right? 30 crore by 300, how many phones you need per day to be manufactured, to be sold? Because India itself has that market, right? And calculate how much we need per second, right? So this is the level in which chips are being sold in the world. And so we really will have a large market. The only thing is we need to come up and we need to do the entire stack. It's not that I will do the design, I'll go somewhere else and do the manufacturing. India as a country must have the complete stack. No question. We'll be design powerhouse, all these things, but fab can be done, why should we? Well, all this is not true from a security perspective. If you really want secure, because your mobile phone you are using, this is a digital phone. Suppose I say you are buying a house, and let's say there will be some 3-4 strangers inside, you have to live with them. Will you go? Will you buy that house? No, right? Similarly, if you are buying, this is your digital home, na? Always, right? Very close to your heart, correct? You keep it in your pocket always. So there is a need for us to do this entire ecosystem in the country. And that is what we have been struggling and we will continue to struggle. And at some point of time, we will take it, we want to do a demonstration. So the recent demonstration, friend, we did a chip along with ISRO. The design was conceived in Thiruvananthapuram. We designed the entire, RTL was developed here. RTL was developed at Chennai. SEL Chandigarh, 180 nanometer. 20 years old but still relevant. We did the fabrication. Then the assembly, as you know, there is one QFN packaging which in the chip on the sides there will be these pins. But there is some ball grid array packaging where the pins can be on the bottom side of the chip. First time ball grid array in India. Tata has the facility, so Karnataka we did that. And then the PCB was designed at IIT Madras, manufactured at Gujarat. Again assembled back here in 2 companies plus IIT Madras. Software written here, booted. From the time the final product came, final assembled product came, we just booted it in 1.5 hours. Okay. So, friends, the entire ecosystem was done in our country. We did not go outside. And that is very, very important. If you don't do that, then we are not in the game. So let us all work towards that. So please specialize in multiple things. Design, specification, architecture, very, very important. Don't neglect it. Right? And we need to upgrade ourselves. We need to start looking at high-level architectures, not the Gavankar 8085 again. Right? We need to look at very high level assembly programming. Lot of embedded code development, application development, that is one part of the story. Then we have to look at extremely complex, very interesting physical design, verification, the front end and the back end design. Then of course understanding the fab manufacturing, understanding packaging, understanding testing, design for testability, digital systems testing, mixed signal design. So all these aspects, I am sure all of you must put a lot of effort and become very, very strong in it. So you will have a great future. And we'll talk about it in tomorrow, today evening and tomorrow. We have Mr. Rajiv Chandrasekhar who will be joining us very shortly. I'll be introducing him. He is actually one of the prime movers for this Digital India RISC-V movement. I'll be talking with him. So I'm very happy that this hall is full. Next time we have to move to SAC, which will be 3 times this capacity, right? And we would like to see more and more participation. Thank you, friends.
We have a hearty welcome to our chief guest of today, Rajiv Chandrasekhar. Welcome, sir. Namaskaram. Please welcome me to the Delivery Symposium at IIT Madras. I'd like to briefly introduce Rajiv, sir. So Rajiv. So last request Professor Kamakoti to please come and introduce the chief guest of the day, Rajiv.
So friends, I am very deeply gladdened today to have Sri Rajiv Chandrasekhar ji amidst us for this RISC-V symposium. Let me introduce him as a CPU architect. I fondly remember going to the ministry and my first meeting. First 10 minutes we are talking about RISC-V project, funding, etc. After that he just asked, hey, what is that cache coherency protocol? Sometime before I learned, can you just briefly tell me about it? And I had the pleasure, first time, it was dream come true for me, talking to a minister about cache coherency protocol in his cabin. I think that is the point where Digital India RISC-V started. He is the man behind DIR-V. So he coined this word, Digital India RISC-V, and he was very kind enough to make a national announcement, like how we have a national bird, we have a national flag, we also have a national instruction set architecture, and this we owe to Sri Rajiv Chandrasekhar ji, so a big round of applause to him here. And beyond that, he had certain action items for all of us. He's a very task man, I should say. Lot of action items that he had in his mind. At least some 50% of that has become true today. And I'm so very happy that he is here, and I'll take some time after this to go and show the stalls where some of his dreams have come true to some extent. But friends, again, we have a very long journey to do. It's just a tip of the iceberg. And I am sure he has a very big global perspective of what India needs to do as a country today in the area of semiconductors, facing some of the very interesting challenges that come from multiple critical emerging technologies and the intervention of AI, and how does semiconductor reflect this and how we need to take forward. I think that's going to be a very important journey ahead, and we are very keen to listen to him today of his ideas and how we need to take it forward. So with this, I again very heartily welcome Sri Rajiv Chandrasekhar ji, and to address this 900 plus people who have come here. This is the largest crowd that we have seen for any semiconductor event in IIT Madras. So very happy to note that. And let us hear from him and see what are the things that are in front of us that we need to take forward in the near future and in the long term. Thank you. So I invite Sri Rajiv Chandrasekhar ji to come and address the audience.
Thank you, Professor Kamkoti, for that warm welcome. And I certainly share his happiness in seeing so many of you here on a Sunday afternoon, which is usually spent watching Netflix or whatever it is that people do, that you are instead choosing to talk about and listen to conversations about RISC-V. And it should tell you that how keen I am to be a participant, that I endured the 2-hour drive to the airport in Bangalore and all the traffic jams so that I could be with you here to share some of my thoughts. So anyway, first of all, thank you for inviting me. Thank you for being here. And I am particularly, personally, very, very happy to see that DIR-V, a program that was launched at the encouragement and support of the Prime Minister, has clocked more than a few cycles, and that we are now celebrating the second summit today here at IIT Chennai. I don't want to bore you with too much, but I certainly want to share some of my thoughts of where we were, where we are, and what are the possibilities of where we could go. And I say this with some authority and some experience to especially those who are students today, that this is certainly the most exciting period in the history of technology. I was at a similar function, not a similar function, but a technology function about a few days ago, and a youngster came up to me, put a mic in front of me and said, "What is it that you most hope for today?" And I said, "I wish I was 30 years younger, and I wish I was a student or somebody just entering into the space, because the opportunities today are just tremendous in terms of the opportunities of almost re-scripting the landscape of technology as we know it, as we knew it for all these years." So I wanted to make that point. This is certainly, and you may think I'm a former minister and so I'm used to overstating things, but I can assure you this is not an overstatement. This is certainly, in terms of the history of technology, one of the greatest inflection points that we today live in. That is the one point I wanted to make. The second point I wanted to make is that India has traditionally, and Indian entrepreneurs, Indian brands, Indian companies have traditionally lagged for the last almost 30 years, 25 years, in the areas of semiconductor, in the areas of electronics. We have no notable architecture, system, solution, component, or device that we have done over the last 2.5 decades. And effectively, we were an innovation economy that worked off of architectures and platforms and systems that were designed, built elsewhere. And we created software stacks, layers of applications around that. And that is what constituted our innovation economy for over 2 decades. But where we are today, almost every aspect of that technology ecosystem, whether it is the component, the device, the system, the segments of the economy that are embracing electronics and digital technologies, and or the software stack that sit on of it, all of this is getting re-architected and redone. So you can today sit and look to the future. So I've talked about where we were and where we are today. We have today the opportunity of being a significant player in scripting the future of device, system, and the operating software and the software stack on it going forward. Because all of this is getting redone. All of this is getting re-architected. These cycles, the technology cycles that we have seen in the past are repeating themselves, but albeit in a shorter timeline. For those who follow technology history, you know that there were these big, large mainframes that then went to minis, then moved to desktops, then moved to devices that were handheld. And that cycle is, in a sense, being repeated and replayed today as we move into the AI age and semiconductor and AI intersect. So we are at a stage, in a nutshell, without sounding too complicated, where everything today, from what is your central processing on a board, what does the system look like, what is the whole paradigm where you used to have operating systems, will large language models replace it? Where we had bits and bytes before, will tokens replace it? Where we talked about cache and memory, will context replace it? So we are almost at an ab initio starting stage of the next wave of what would be the future of technology and future of compute. And that is where we, India, and all of you, some of you, most of you, can play a very significant role, including with the RISC-V ISA and the DIR-V program. When DIR-V was launched, there was no semicon in India, there was no semicon policy. But there was a dream, there was a desire on the part of our Prime Minister, and certainly it was something that I wanted to happen as well, that India move from being completely absent from semiconductors to having a presence, both in the design and innovation side of semiconductors and chips, as well as manufacturing and packaging innovation. From 2021 to now, if you look at it, we have moved from being a complete absentee in the semiconductor landscape to now today slowly and systematically building, planting our flags and building our presence. I have absolutely no doubt by 26, 27, we will have our first 28 nanometer fab in Gujarat. We will have multiple entities doing packaging innovation in India. And along with that, I am hopeful that the DIR-V ecosystem will continue to expand and grow out of the lab, out of proof of concept, into creating real commercial success and real commercial applications and system where RISC-V and DIR-V devices are embedded. So this is the dream, this is the hope, and this is certainly something that is achievable, and therefore let me share as the last part of what I will want to say today, what I believe the RISC-V ecosystem roadmap should be, or what it could be. We have spent a lot of time in our country, and I say this with all respect to everybody who's a practitioner, of building technologies that then go looking for a solution. It is personally satisfying, and certainly in many colleges, universities, labs, there is a tendency to build a chip or build a system as a proof of concept, as a demonstration of one's capability. But then that goes nowhere because there is no commercial application of it, or there is no commercial ecosystem into which it is embedded or transferred. So my real hope for the next year of DIR-V is that we will now build devices in closer partnership with the ecosystem, the tier 1, tier 2 product manufacturers or product companies that will then take these devices and embed them, or vice versa, have systems designed around these devices. So I think a closer partnership between what is out there in the electronics ecosystem and the DIR-V ecosystem is one important milestone that we must deliver on. The second is DIR-V. The narrative around DIR-V used to be, no, this is not going to do high performance, this is really going to be for controllers, this is only for lower end of the market. But DIR-V is today representative of the power of open source, both in AI and in semiconductor. We are stepping into an era where open source AI, pre-trained, trained models that are available in the open source will be used to create, with inference, create expert models. At the same time, there are many, many shops around the world, including in China and in the US, where RISC-V is being deployed for high performance applications and high performance use. So therefore, my own second expectation of the DIR-V ecosystem is that we move up from, and as Shakti has shown, move up from the microcontroller category, the generic category, to more and more of devices and components that are in use for, or that will be used in this emerging AI ecosystem. The third is that, again, this is about, I'm addressing the issue of problem looking for a solution, is that we do more and more pin-compatible functional replacement of existing chips with DIR-V chips. That we design DIR-V products, DIR-V devices, that to be pin-compatible and replacing existing chips. That will tell us also that we are competitive cost-wise, that we can create market share in categories of chips and devices that are already existing, rather than only depend on new markets and new applications like AI. So that's the third. And the fourth is, I think this is something that Professor Kamakoti will certainly appreciate because of the hypervisor work that has been done in IIT Madras, is that as we look to the future and as we look and understand and acknowledge the fact that the software architecture, the software ecosystem around devices and systems is also rapidly altering, with large language models and AI models and agentic AI that are going to change the way that we look at compute. Can we also look at, in the DIR-V ecosystem and the DIR-V roadmap, something that is a RISC-V operating environment that is at a higher level of abstraction than hypervisors and just a plain old operating system? So there is this opportunity, in my opinion, as we talk about, will the LLMs replace operating systems? Will iOS and Android be replaced by something that looks like and speaks like agentic AI on your devices? Can we create a software stack or an answer to that around DIR-V and RISC-V? So these are, according to me, and obviously I'm not a graduate of IIT Madras and I defer to the wisdom of everybody else who studies here and who teaches here, but I think clearly these are opportunities that are available, that are real opportunities, and these are global opportunities for us. I was at the, and I'll just end by sharing this thought with you, as I was at the France AI Action Summit, and there are multiple conversations that are today currently happening, multiple threads. There is this thread about AI innovation and where will AI go, how fast will AI reach AGI and ASI and singularity. Then there are these threads about AI and what should be the governance of AI, what should be the guardrails of AI, how can AI be prevented from misuse. And then there are some emerging commonsensical threads around AI and semiconductors about what really is the economic benefit of AI. How will that economic benefit be unlocked? and what is the role, what will be the model as after the DeepSeek moment that will intersect innovation and economic benefit. And as recently Satya Nadella said, what really actually is the use case for AI? Is it edge AI? At the core, what is AI and what will all that compute be solving? So what is the use case? So there are many of these threads, and these threads will continue to grow and accelerate and amplify. And like I like telling everybody of an example about how everybody today is excited by semiconductors and AI. I spent a 16-hour flight from Dubai to Brazil. The government of Brazil had invited me to a 3-day workshop on AI and DPI. And so the lady cabin crew, the stewardess, asked me, so why are you going to Brazil? So I said, I've been called there to talk about AI. And I kid you not, she held me captive and gave me a 15-hour one-way dialogue, one-way monologue on AI on that 16-hour flight. So the fact is that everybody, even if you're not a master's student or an undergraduate student or a postdoctoral or doctoral student, around the world is extremely excited about what is happening in the coming months and years. And I think, and I respectfully submit to all of you, that for the first time ever in the history of technology, as I know it and as I understand it, we have a tremendous opportunity as India, as Indian students, as Indian entrepreneurs, startups, and academic institutions to build things that are really going to shape the future of semiconductors and AI, and therefore the future of tech and the global economy as we know it. This may sound like hyperbole, but it is not. It is future as I see it. And as I said before to you, I have a little experience, and therefore do give me some credibility and when I point in that direction. So I wish you all the very best. I certainly wish the DIR-V ecosystem continued growth and continued success. And I look forward to engaging with you again, hopefully not next year, but sooner, in seeing how much progress we've made in building products and devices for the future. Thank you. Jai Hind.
So the most awaited, the hackathon results are here. May now request Lavanya to share the hackathon results.
Welcome, sir. So we are ready to announce the results. I also invite Hitesh from NXP Semiconductors. The first hackathon we did is on system software. It's a hackathon jointly organized by NXP and Vyoma Systems. And we are announcing the results. Can we go to the next slide? So we had heard these presentations in the morning. And the first prize winner is Arnav from IIT, BHU. Arnav, are you here? Please come first. First prize. The other prize winners, be ready. He's a second-year student, sir. He did the hackathon single-handedly. It was evaluated by the team at NXP Semiconductors. Thank you. The second prize, Soham, Suman and Dhruv from DJ Sangvi College. The challenge was to performance optimize the core marks benchmarks and also do code size reduction. So they are the team from DJ Sangvi College. Third prize students, please be ready. Mahati and Joshi Aishwarya from Nitte Meenakshi Engineering College, Bangalore. All the other finalists, please be ready. I know who you are, and you also know. Next slide, please. So we have the finalists, the others who were participating, who did good work, but didn't make it to the top 3. We invite all of them together on stage. Sumuk, Vajra and Nivedita, RV Institute of Technology and Management, please come on stage. Priya and Shreya, IIT Kharagpur. Jayesh, the National Institute of Engineering, please come on stage first. So this is only the one track that we have finished. I think chief guests have a lot of work to do. I invite Gopi for the next track of hackathon that happened. So it's over to you, Gopi.
So next track is on Shakti FPGA hackathon. That's the first track we did with the FPGA board. As everyone knows, this happened for a continuous 48 hours, 2 nights. Actually, it is 3 nights for us. It happened, and next slide. The winners are first prize from Banariamman Institute of Technology, Gautam, Manoj, and Kaushik. They are from the second year. They did the excellent problem solving for the maze. They were able to crack the first mini maze also, and they were able to go to the second biggest maze of size 3x3. Next, the second prize, Mosphere from SSN Engineering College, Ajitish, Sriram, Vineet. A second prize from SSN, Ajitish, Sriram, Vineet. They did the robotic arm, the second problem statement. One of the creative team that we see. A round of applause for them. Third prize winners, please be ready. Arduino is gone hereafter. Only Shakti is there. So third prize from Shastra Deemed University, Sastha Rajan, Raghav and Balaji from third year. These are also from solving the maze. There were a lot of restrictions with this problem statement. One was the board size, which was nearly 13-inch, and everybody were able to bring up the entire, they were able to struggle a lot and brought the solutions up. Next, the fourth winner. Yeah, the fourth winner is from Amrita School of Engineering. I could say that their design were not able to get through, but the best design we have seen there. They were able to keep the board not like this. They were able to keep they have designed and kept the board like this, just for grazing the maze. It was an excellent idea. Thanks.
We have 2 more tracks. Kunal, please come on. Okay, Balaji has come on stage. So he has done core enhancements, the actual design enhancement his students has done. So he did.
So I will start with the third prize. So third prize goes to team 2. Congratulations, Indra, Adi and Aravind. Yeah, the project is about core enhancement. So what it does is to design a systolic array, accelerator and maker-chip platform, which is like TL Verilog, which is an extension to Verilog. So what it does is you design a systolic array, compare with CPU and try to see what is the speed up with the accelerator performance. Yeah. So students got up some around 15 to 20 times of speed up compared to CPU. Yeah. So I will announce the second prize. Second prize goes to team 3, Anushka, Sandeepan and Vansh. Congratulations, please come to the stage. So announcing the first prize winner, it goes to Mithun and Preetham. Congratulations, please come to stage. Sorry? Yeah. So the additional stuff they have done is they added specialized adder and multiplier. So they implemented Cogestone adder and Velocity multiplier to the code, which gave more significant improvement in the performance.
So the final and a more important switch track is from solutions to product. So the final is the product track. I'll hand over it to Kunal to announce the results.
Good evening, all of you. So my screen. Rajiv sir and Kama sir, do you remember this pic? So this was the first product-based skilling program that was launched by you. So now from first one board, we have now 5 boards. Yeah, and so all of you should thank who have done the products. Should thank Rajiv sir because it was his idea to make the product-based skilling program famous in India. All right. Okay, so I'll switch to the first prize. Sorry, third prize. So the third prize goes to PSG College of Technology Energy Efficient System for Electric Motors.
The products are displayed.
Yeah. So it's basically measures the vibrations and basically controls the vibration based on the what is the amount of vibrations controls it. It's basically a vibration controller for the motors. Okay, congratulations. The second prize goes to Sri Ishwar College of Engineering, and it's an IoT-powered smart home automotive systems. It's built on Vega Iris boards. So Sri Ishwar College of Engineering team, Vishnu Vardhani and all of you, and please come. Yeah, and finally, the first prize goes to Sri Satya Sai Institute of Higher Learning on dual axis solar tracker system. Congratulations, the team, whole team. And all the other product teams, can you please come over here? All the other product hackathon teams. The remaining teams, can you quickly come on the stage? Fast. Run, run. Yeah, quickly run, all of you. All right, so all the remaining hackathon product teams, can you please come on the stage? And so the remaining top 7 finalists are on the stage. Yes, please. So these are the remaining top 7 finalists. They also deserve a huge round of applause. You know, out of 70 teams, 10 teams have been landing at IIT Madras team. And it's all because of Rajiv sir's product-based skilling programs. Okay, thank you so much. Have a great evening.
May now request Professor Kamakoti, the Director of IIT Madras, to honor the guest with an Angavastram and a memento to Sri Rajiv Chandrasekhar, former Union Minister of State for Electronics and Information Technology. Ladies and gentlemen, boys and girls, please give a round of applause for our chief guest, Sri Rajiv Chandrasekhar. Thank you so much, sir. It's a pleasure having you here at IIT Madras.
Good evening all. So it's my pleasure to welcome our next speaker, Hitesh Garg, who is the Vice President and India Managing Director for NXP Semiconductors. He leads the India business operations across all the 4 sites in India, namely Hyderabad, Pune, Noida and Bangalore. Hitesh also serves as the R&D leader for AMS Competence Center in NXP. In his technical role, he is responsible for building world-class analog and RF products. And his teams in Netherlands and India design IPs or subsystems in the areas of security and connectivity, ADAS and smart car access. Hitesh has more than 25 years of development experience in analog and mixed signal designs. And prior to NXP, he has worked in Connection Systems, Microchip, and state-owned Semiconductor Complex Limited in various technical and leadership roles. And Hitesh holds a bachelor's degree in electronics and communication and a postgraduate degree in management from IIM Bangalore. So it's my pleasure to welcome our next speaker, Hitesh Garg. Welcome, sir. Welcome to IIT Madras.
Hello everyone, very good afternoon. So I think it's a great privilege for me to address this audience, and especially Rajiv ji is among us. So Rajiv ji is a visionary who showed us the way how India can make a big step in the field of electronics. And I think whatever progress that we have seen in last 3 years, where we are in terms of not only design, manufacturing, it's all because of his vision and I think the efforts that he has put, especially in institutes like ISM. So big thanks Rajiv ji from core of our heart, so for taking us forward, for showing us the vision. At the same time, I think as Rajiv ji mentioned, the world is changing around us. The world is constantly changing. So we were like an analog world in 2000 and 2010 we moved more to the on-demand world, but now we are getting into robotics age, right? And that's where I think one of the key things that we need to see, incumbency is nothing, right? You can start from very fresh without knowing what has been done in last 20 years. You start very fresh and you can really win the game. So I think the new age models, the new age thoughts, they have kind of lived their life. So we are into this new age, robotics age, where we talk about edge devices, smart connected devices, AI, that is showing the way in front of all of us. And there are applications, right? And there are applications everywhere in robotics, in healthcare, in automotive, building automation, power and energy. And I was so nice to hear that a lot of solutions which are built on RISC-V, they are around these applications. The more we have our approach towards systems, the more we have our approach towards these applications, the more we aim to change the world, I think the better success rate that we all can have. So I think these are the applications which are definitely as a challenge in front of us. At the same time, right, there are also certain needs. So when we talk about secure edge, it is not easy. The technology on one side, it is giving opportunities, but there are huge challenges. So what are those challenges? When you talk about edge AI, we want low power solutions. We want ultra low power. We want, because we are depending on those solutions, we want those solutions to be functionally safe. Again, system security is one of the topic. Real time. We want these solutions to be working real time. If your car is running at a 200 kilometer per hour, you want the systems to be running at the same speed. Because if there is an autonomous car which has to brake after running at 200 kilometer per second or kilometer per hour, so then it has to brake in the real time. So the systems have to be built in the real time and secure connectivity. Nobody should hack the car when you are running at a very high speed. So I think these are I would say the challenges which are there in front of us from the technology perspective. And as we enter the world of AI, right? So what we see again, these are, I would call again, opportunities, autonomous systems. We are looking for sustainability, of course, connected and sensing, and resilience and efficiency. And that's what we call as edge AI. That's what we call as an opportunity in front of all of us. But this looks also very complex. So many applications, so many technology vectors. There is a hardware, there is a software, there is a system. Where do we start? How do we kind of reduce this clutter? How we as an engineer, right, how do we think? So we have, I would say, if I have to reduce the complexity, I can divide it into three pieces. One is the hardware foundation. Second, we need to think from the technology requirements. And the third is mainly on the application level software development. If you talk about hardware, of course, there are various complexities of microcontrollers, microprocessors, analog, power management, sensors, connectivity, right? So which is in front of us, which I think if you are an hardware engineers, that's the bottom line that you will look at, right? So Honorable Minister even talked about, okay, what should be the future of RISC-V? Yeah, get into high performance compute. So of course, we have kind of shown how RISC-V can help us in the microcontroller kind of an era, but how do we get into the high performance compute? How do we get more into AI kind of applications using RISC-V? Then we also need to have technology pillars, right? So again, connectivity, vision, sensors, touch, voice, security. I think these are the technologies that you also need to enable with your hardware. The third is on the softwares, on the solution level, reference design, proof of concept, software packs. So more and more our world is going to be defined not in terms of components, not in terms of chips, but more and more in terms of systems. So I think as an electronics engineer, as a software engineer, put your thinking more and more towards systems. That will make things easier for you to understand, that will make things better for you to win in the market. Again, I'm giving just one simple example, just on the 3 axes. So basically, this is a 1500 battery energy storage reference design. If you can please move up. So this has all the 3 components. There is an hardware. There is also a functional safety, which it should be 1500 battery pack. It need to be fully functional because or fully functionally safe. On top of that, it has to have a hardware which can. On top of that, it has to have software which can look for various applications. So I think this is a product-ready design. Unless we touch upon all those 3 vectors on hardware, on key technologies, in this case it's a functional safety, and on the software, I think we cannot win the market. Moving ahead on the next slide, if you can so I think this is just a quick update on what kind of variety of processors that you can have. On MCUs, at least this is my portfolio for industrial and IoT microprocessors. We have MCX N, A, C, L, and W kind of series. Then we have a crossover microprocessor, which is not application processor, but not even MCU, so somewhere in between. And these are i.MX RT700, 1180. And then application processors, which have multiple cores, and these are the cores that you can see. i.MX 9.3 is also having multiple cores. So this is more of the things, and again there are more requirements coming in. We are coming with more connectivity kind of chips, which is 969. So that is still under development. So even when we talk about industrial applications, so you need more and more high power in terms of application processors. When we talk about automotive, it is exactly the same. You need a scale, so here you see the processor going from S32K1, which is a 90 nanometer chip, to a 5 nanometer, which is a 32N. So you need a scalable compute. You also need functionally safe and secure middleware. You need time-sensitive networks, the networks which are high-speed networks inside the car, at the same time system power management. So any of your solutions that we are building, you need to have scalability, and I think that's going to be the key. And that's what we think of before we start cooking our solutions. If we move to the next slide, please, then you can see that not only microprocessors, but at the same time, the superior sensors, superior sensing is also a key for the product development, for the system development. And we can take some of the clues from, I would say, these characters. Many of you will be knowing, right? So how can I sense moving things around me? How can I sense more of a telepathy or X-ray vision? So if you move around, so again, all these solutions can be through our technology vectors. So there is an ultra-wideband which creates a very high accurate location awareness. There is a V2X, which gives you kind of what is happening in the 1 kilometer square or 1 kilometer radius. There is high resolution radar. So radar technologies are also going very accurate, very much better. And on top of that, if there are various connectivity standard, how you make sure that everybody talks the same language. And that's where Matter is coming with the language harmonization. So I think this is just to give you a kind of a perspective. On one side, scalability on processor platform. On the right hand side, you can see on the connectivity platform, right? All kind of connectivity, Wi-Fi, Bluetooth, Thread, ZigBee, ultra-wideband, NFC. But all this has to be scalable, secure, robust, fully integrable solution. And again, as I said, think from the systems angle. Again, there has to be somebody which is kind of overlaying, and that's what we call it as a software. Again, when my customers come to me, they don't ask that I want this kind of chips. Of course, sometimes they come, but they are looking more and more from a platform. So I think we as a chip companies, we are also starting to think in terms of systems. How we build system, how can we create our offerings, which is more in the system levels. So I think this is Core Ride is more of a platform which we call it as an SDV platform, which is a software defined vehicle. And software defined vehicle, it integrates all kind of networking, compute and power management capabilities and creates a middle layer. On top of that, application layer of course can be defined by the customer, by the OEMs. But I think with this Core Ride, we enable our customers to come with the solutions much faster in the market. If we move again in this, one of the key resolution, and here we are in the RISC-V convention symposium, I think it is the revolution. It has a big part to play in this whole evolution of compute in all angles. And we have seen that there are shifts, there are systematic shifts happening in that direction. RISC-V cores are taken more and more seriously. They are replacing the existing cores that people were using. Even yesterday there was an announcement from Alibaba that Alibaba is Jack Ma's company, most of you know, that they have recently they started a company, but they have announced a RISC-V high performance compute core. So they have already come up and they are spending quite a lot of money on that, but not only spending the money, but they have come with solutions which are ready for us to be used and deployed. So I think RISC-V, it's a parallel development happening all across us. So there is a huge potential that we see I would say in the edge AI. So I would request, I would suggest, I would encourage all the developers here to see how we can make use of the potential. So come up. I think the world is running at a much faster pace. I think the only request is that we have to move much faster. If we move, I think we are already using, even in the 5 nanometer SDV platform, we are using some of the RISC-V chips, which are based on our own RISC-V platform. And of course, we are using mainly for the security purpose, security application. Then if you can move, then this is also one of the secure A30 authenticator that we have. So this is also based on the secure RISC-V. In the last example which I have is for NFC IC. So basically secure element based product portfolio which we have, which has NXP security hardened on the RISC-V CPUs. And again, this is the first NXP product which was based on the RISC-V, and we have more and more NFC based product which are utilizing asymmetric and the symmetric crypto. So overall, I think this can be used as a security device, this can be used as a low-end compute device, this can be used as a high-end compute device, this can be used as edge AI, MPU, NPU, whatever possibilities that we have around us. So I think, again, as I said, the possibilities are humongous. If here I try to cover my story. So we are transitioning from machines to secure edge devices. And I think these are the 4 things that we need to have. Of course, hardware is important. Architectural transitionings to rework the whole brain. And I see RISC-V has a huge capability there. Superior sensors. And again, sensors, many times the sensor chips are not only a pure sensor, right? There has to be some compute. And that's where also RISC-V can play a very important role. Built-in trust, AI, machine learning plus deterministic real time. So I think here also RISC-V can play a role. And the last is whatever that you do, the toolboxes, the software, I think that we also need to see that how we integrate our solutions, right? So looking at all these 4 vectors, I see RISC-V has a huge potential. The way we are moving people are asking, okay, do we need more GPUs or do we need more NPUs? It's anybody's guess, but if somebody asks me, I would say NPU or TPUs have a more potential because they are solving our solutions for the secure edge, and there are many more applications on the secure edge, on edge AI, than in the data centers. So please come, innovate. There is a word in front of you. Thank you. Thank you very much.
Yeah. So we'd like to thank Hitesh for the invigorating talk, talking about the portfolio of NXP and also NXP's foray into RISC-V and motivating most of you to take up building products for this ecosystem. So thank you, sir, once again. And we are privileged and pleased to have you as a part of the symposium. Thank you. So we have a couple more talks, but we also have the ex-union minister. So the startups here, including CDAC, Mindgrove, they're kind of with our ex-union minister to exhibit their products in the stall. So I do request the audience to stay put for the next 5 or 10 minutes until our speakers come back. So we're going to have a talk by Shashwat, CEO of Mindgrove Technologies, and also Dr. Krishna Kumar Rao from CDAC. So we're waiting for 2 good talks. I'm pretty sure they have a lot of interesting information to share. So please bear with me. Please stay put, and we'll have them soon once they are done exhibiting their product to our ex-union Minister of State. So I'd like to request you to stay put, and we'll have our talk soon. Okay. Good evening, everyone. So we'll have the next set of talks. I'm pleased to introduce T.R. Shashwat, who is the CEO and co-founder of Mindgrove Technologies. And anyway, I'm extremely pleased to introduce him because Mindgrove was my first employer back in India. So it's a unique honor for me to introduce them here. So Shashwat is an accomplished electronics engineer. He holds 17 years of experience, in non-destructive testing for critical industries that include aerospace, oil and gas, and nuclear power. He's an alumnus of SRM College of Engineering, if any of you are from there, and driven by a strong passion for hands-on learning and innovation. Shashwat, along with Sharan, they co-founded Mindgrove Technologies, who are here to build and help develop this RISC-V based ecosystem in India. So Shashwat, please come on stage and we'll be happy to.
He is one of the pillars of this whole program in IIT. So I'm Shashwat, I'm CEO of Mindgrove, for those who don't know me. For those who know me, hi. And for those who don't know, we are the people who take all of the cores and the SOCs and make actual silicon out of it. We design the silicon, we take it to production. This event is happening at home for me. My office is just 3 floors down. All of our SOCs are based on the Shakti processor, which was developed, a few hundred meters that way. And so today, in the presence of Kama sir, I would like you to come and help me release something very important to the world. I want to just unveil this, which is the first development board which we are taking commercial of the secure IoT platform that we built. Sir.
All the best.
Thank you, sir.
I must congratulate Shash and Sharan and the entire team for bringing this up. You know, in running a semiconductor startup in Chennai is actually a most Herculean task, and it requires a lot of courage. And what we are seeing is the display of such a wonderful courage here. It must be a big motivation for all youngsters to take up semiconductor as a profession, as a startup. And I'm sure this board should see the light of the day, should find several millions of customers. I wish you all the best, Shash and Sharan, and let us continue this journey. Yes, thank you very much.
So, today I have revealed this board, which took a whole year after getting silicon for us to actually get to the point where we are comfortable taking it and handing it to a customer, to a student, and saying, do what you want with it. Unfortunately, we were just a bit too late to get it into the hackathon, so bear with us. Next time an event like this happens, I hope you will be able to use Mindgrove boards. This will be going into actual shelves where you can order later this year. But having done this, where we are moving out of all of this, I just want to take a look back and then look forward and think of everything that we've achieved and what all it is required for us to work and go forward. RISC-V is teenage now, right? It started in 2010. The first silicon from India happened in 2018, 2021 with Rice Creek and Tejas. And then what have we done after that? Where do we go from here? What do we need to do from here? Rajiv ji gave us a lot of great pointers in his talk. And with his permission, which I have already taken, though he's not here, I am going to go forward on all of those things, and I would like to make it known that his vision is something that is shared by other people in the community. We are moving out of the lab, and we are moving on to the prototype stage. And when you're doing that, there are certain things that come to fruition, right? We are going to a customer, you're going to a developer, and you are asking them to use your chip. My thoughts are focused on the direction of users and customers, not necessarily just on the design and development of a processor. So what can we do to solve all of their problems? How do all of the problems in the real world impact the way that we design? How do final requirements inform the way that we engage with the ISA? What kind of extensions do we need? What kind of stuff do we need to work on? How do we communicate our position, our solutions to the users and to the rest of the world? And like I said, we've been at this for more than a decade, and you've seen Google announce that sometime last year they announced that they're something about RISC-V and Android, they're taking a step back. And we all know that open architectures are more secure. We all know that with more engineers looking at security, it is better. With enough eyeballs, all bugs are shallow. All of that we know, but how do we communicate it? How do we make it? How do we take that forward? You look at, that quote was from Linus Torvalds, and Linus's biggest achievement, I think, beyond the Linux kernel, beyond creating Git, is being able to take that to the user, and it is deployed on most of the phones today in this room, right? Android is based on Linux. How do we recreate that? How do we learn from all the people who have come before us? Where is the revolution? RISC-V is already shipping. right? I said there is nothing between 2021 and now, we are not shipping anything. But then RISC-V is shipping. It's not like RISC-V is stayed stable. I don't know how many, most of the students here would have used this particular board, right? ESP32 C3. C3 is a RV32 board. Beagle has a T-head chip on it, Beagle 5. There is a CH32-5, which is again a Chinese chip. Tiny microcontroller, costs less than 50 cents. And these are being deployed in their billions. Recently, we even have a laptop board. I don't know if anybody's heard of the Framework laptop, which is like Lego blocks for building a laptop. And very recently, they've released a DC Roma board, which is based on a Chinese chip again, a JH110, I believe. What can we, as the DIR-V community, do to make all of this happen in India? Annual shipments 3 to 4 billion, not one is an Indian chip or an Indian core. I don't know if there are Indian cores, but definitely not an Indian chip. 80 billion cores by 2026, we want a piece of this in India. Standalone processors, microcontrollers, custom implementations, FPGA, whatever you name it, RISC-V is everywhere right now. There are RISC-V chips inside your Android phones, by the way, today. They're running your cameras, they're running other sensors. But this is the bad side. This is a JH710 board, Vision 5.2, and this is a blog post by a very well-respected electronics reviewer on YouTube. It was hard to bring up. I had to dig through forum threads, and then I finally landed up in a blog post to figure out how to update firmware. Upgrading firmware involved in running a special build root image, logging in with SSH. I had trouble with the HDMI. GPU handles 4K, but I couldn't get it working on a HD monitor. This is the kind of stuff that happened in 1990s when I was dealing with Pentium 1. This is not acceptable. As a community, these are the things we like to talk about, right? We like to talk about fragmentation is one big thing that everybody talks about, especially the bigger companies. RISC-V is fragmented. RISC-V is open source always fragments. RISC-V, there are so many implementations. I have not seen a customer ask me about the fragmentation. You have people talking about addressing modes. You have to, are you using BlueSpec or are you using Chisel? Are you using System Verilog? Nobody cares. We care as a community. And those decisions impact the way that we build our software, build our hardware, build our software, build our systems. Nobody cares about the 5-stage pipeline, right? Whether you have a 5-stage or a 12-stage pipeline. What do they really care about? They care about performance, yes, but they care about all of these other things. Raise your hand if you've run across any of these questions. Where is the RISC-V SDK? Does your chip have an SDK? Does your board have an SDK? Where is the IDE? What kind of IDEs can I use? Sir, you can use any IDE, all of them work. But where is the IDE? Okay, here. I have to build it for you. Okay, fine. I need reference designs. Texas Instruments is the past master in building reference design. Learn from them. Packaging. Everybody asks me, is your chip available only as a BGA? Can you create a QFN? Can you create a QFP? Can I use 70,000 rupee, 1 lakh, 2 lakh, 10 lakh Seger or Lauterbach debugger that I bought? Can you give me a development board? As of today, the answer is yes, I can give you a development board. What kind of software do you support? What kind of boot sequences? What is the boot sequence? You saw that with Jeff Geerling's article in the previous slide. How do I boot this damn chip? If we don't have an answer to that, what are we doing? Will your company be around in 10 years? Most importantly, do you have documentation? The answer for most of us is no, we do not have good documentation. And you know what a lot of people ask me? Sir, your chip is really good, we are interested, but then we are buying this board from China. This is a Pixhawk, this is a flight controller. We are buying this board from one Chinese manufacturer. He gives it to us, we just put it in our whatever our device is. It could be a vacuum cleaner, it could be a drone. We put it in, we plug it in, everything from software is there, sir. We just have to do a configuration, everything works. I don't like that. That is horrible engineering, but then unfortunately that's the world we live in, and we need to serve our customers. So what are we doing to build this kind of hardware that people can quickly adopt? And what kind of other things do people need to adopt RISC-V? I'm going to tell you a story. This is not about RISC-V. This is about ARM. Samsung used a MediaTek chip in a phone. And then there were some researchers who came up and broke it. This particular chip secure boots. This particular phone has the secure boot properly configured as MediaTek intended. They had these problems. This partition, that's the boot partition, contains a signature. It is not verified at boot time. It means that somebody has the ability to write anything to flash storage, can compromise the flash storage. How did they compromise it? Not through some fancy, not through breaking the security directly. They compromised it using a JPEG parser, which executed code for some reason. Now, this is the wanted ARM trust zone running. This is the pinnacle of software security, of system security today. It doesn't have to be this way, right? It should not be this way. I recently ran across this particular thing. This is called multi-zone security. And what it does is it uses, guys, it doesn't even use the hypervisor. It uses PMP, just physical memory protection. If you have n physical memory zones in your processor, it just divides the world into n. And you can have zone 1 running your application. Zone 2 is a secure something. Zone 3 completely independently runs on your network stack. And let's say zone 4 is an monitoring core. You can split your peripheral so that something that needs to be secure is separated from something that needs to be that can be user visible. So you can separate your Ethernet controller from something which is say running flash. It runs just on PMP and a microkernel running under PMP. It can boot a Linux on one zone, it can boot a RTOS on another zone. Amazing stuff. This is done by a company called Hex-V. Hex-V, you can go up and look up their talks in the last few RISC-V summits. It was really nice to look at it. It was the first time I understood exactly what ARM trust zone is, and it turns out that it's exactly one wire, by the way. You're in Chennai now. So, a little bit of Tamil Nadu pride. I swear this is going somewhere. This is Mahabalipuram, which is one of the biggest symbols of our state, right? And in Mahabalipuram, we talk a lot about it. It's something that we're very proud of. But Mahabalipuram has a secret. And I'll tell you what that secret is. These are two of the most famous monuments over there. Unfinished. These are just carve-outs. That is also, the 5 rathas, not one of them is finished. Unfinished, completely unfinished, everything. Hex 5, I told you there are some really great talks, 2018, 2019, 2020, 2021 maybe. And then they disappeared off the radar. I don't have a website for them. I don't have contact information. There is a GitHub repository, some talks on YouTube, and a patent. Where are they? How are they contactable? For heaven's sake, let's finish the project and let's get chips into the hands of customers. Thank you.
Okay, so I'd like to welcome the last speaker for the day. It's Sri Krishna Kumar Rao from CDAC. Sri Krishna Kumar Rao holds a bachelor's degree in electronics and communication from the College of Engineering, Trivandrum, and an MTech in microelectronics and VLSI systems design from IIT Madras. So he has over 30 years of experience spanning system architecture design, RTL, functional verification, physical design, hardware testing, system design, and IP core design and verification. He's right now a senior director at CDAC, and under his leadership, his team executes various projects in microprocessor design, FPGA or ASIC design, embedded systems, and a lot of IPs. So, sir, we're happy to have you here, and we look forward to your talk.
Good evening to all, very good evening to all, and thank you, Kama sir, for holding such a great event and calling us and inviting us and giving us an opportunity here to speak. So I want to take what do you call, in Malayalam we say jamyam, or I don't know what equivalent to say, that I'm going to give standard stuff, okay. So there's nothing revolutionary in what I'm going to say. So I'm just going to tell you on what work we are doing, and in DIR-V what is happening in as far as Vega is concerned, and what is the stage we are in, and what is the way ahead. So couple of slides on CDAC. So those of you who are not aware of CDAC, there are a lot of youngsters here. So CDAC is an R&D organization which comes under Ministry of Electronics and Information Technology. So we are spread across 12 locations across the country. So we work in multiple areas. This microprocessor, what I'm talking about, is only a very small part of work we do in that domain. There are a lot of other areas we work in. We work in supercomputing, we work in health technologies, we work in strategic electronics, we work in power electronics. We have teams working in language technologies. So there is a whole range of activities which CDAC works in. So why I am saying this is I see a lot of young faces here. So CDAC is a government company. There are a lot of private companies, a lot of opportunities are there, but still some of you can, we take people every quarter on a regular basis, advertise, and we pick people. So some of you, I would request to go through our website, find opportunities, and one thing can guarantee that the pay which big companies pay, CDAC never pays, but the kind of work which happens in CDAC, there's real good work happening. So I would request the young audience sitting here who are going to graduate soon to look at it and see if it makes sense and apply, and we'll be happy to have you with us in our teams. Not my own team, there are multiple teams across centers working in many areas. Even quantum, we have people working. So there's no dearth of opportunities for the right minds and right people. So I think I covered this slide. So this captures kind of the areas we work in. We work in EVLS, embedded systems. We work in professional electronics, under which many things fall. So as I mentioned, there's power electronics, there's control instrumentation. So there are big teams which work in all these areas. So you have all these multiple activities happening under one umbrella. So that would cover a good spectrum of things happening in the electronics hardware as well as software. So I come from the hardware design group, where we focus on the activities you see here. We work on processor design. Again, that's only one part of what we work. We work in ASIC design, FPGA design. We work from spec to RTL to GDS2, or in another case, it can be from spec to RTL to an FPGA-based solution. It's not just a solution. We build PCBs, we build boards, then we build products also. So there's a host of activities we work in. And what I'm going to talk about, microprocessor design, is part of the activity we have been doing for the past 6-7 years. We have been focusing, one of the major focus areas has been in processor design, which we will come to now. So I think my speakers who came before me spoke about the Digital India RISC-V program. So the Digital India RISC-V program was launched by MIT with IITM and CDAC as the main participating institutions from the government side, to enable creation of microprocessors for the future in India as for the world and achieve industry-grade silicon. And I am happy to say today that many startups, which Kama sir spoke of, has spawned out of IIT, and there are other startups also who are engaging with us as well as IIT, and we have companies who are on the way to build silicon, who have built silicon or on the way, so that at least I believe that maybe in if not in 2026, by early 2027, we will see, that is maybe around 2 years from now, we will see products which are going to scale or go into volume. So that is what I believe, and it's a big thing. Like just now before me, Shashwat kind of, I would say, what his talk captured the essence of the challenges we face. The same thing what he spoke of, we also face, because you build something, you have a silicon in a particular solution you have, and you say you have a development board, let us say, somebody will come and ask, do you have this interface? Oh, you don't have that, is it? Why don't you have that? And why don't you have this? So you build something, there will be n variants available. So people, whatever you don't have, people will come and ask, oh, if you had that CAN interface, it would have been great, we would have found it useful. You don't have that, right? Okay, sorry boss, we don't have that. Right? See, the point is we have to start somewhere. There are companies who are doing great, but they have done that so many years. And it's not an easy thing, like Shashwat was saying. It's very difficult to build these things, verify it, validate it in hardware, make it work thoroughly. Because being a processor, the person who is going to use it, he can run whatever application he wants to run. Anything under the sun can be run on that, right? Literally, the instructions can come in any sequence. And this thing has to work. And you don't have a luxury, like Kamar sir said, somebody reports a bug and you can't go and fix it overnight. It won't happen like that. So you have to make sure that it works, and ideally should work right the first time. Because most of the work we are doing, we don't have that huge bank balance or the huge kitty of money sitting there, so that you make a fault one time, you can go and pay the NRE costs, which run into tens of crores, of at least of the order of 7-8 crores. If you are going for advanced technology nodes, you may end up paying around 7-8 crores for one tape out, just the NRE cost for an MBW run. So we can't afford that we did the first time, it did not work, so we'll go and do the patch whatever we need to do and rebuild the design a second time. Most cases, you won't be able to afford to do that. So it's not an easy thing, whatever we are doing. So coming back to the program, the objective is to design and manufacture a world-class RISC-V process and foster collaboration between academia, startups, and industry to build a robust semiconductor ecosystem. So I believe that is happening now. As our former minister was saying, he started that. Kama sir was there driving it, and I believe it's happening now, because the ecosystem is strong, getting stronger, and we have been able to engage industry, and industry have slowly shown confidence and adopted the designs we are building. So that's why I'm confidently saying that in a couple of years' time, if not earlier, we will see real products in silicon which are going to scale and go into volume. Not, I would say, in tens or hundreds, but at least 1 lakh plus I hope to see in the next 2 years. And the advantage we have is it's an open source ISA, so it gives you the flexibility. You don't have anybody to pull you down or tomorrow come and catch you. You can't go and, I mean, from an academic perspective, I can very well build an ARM, take an ARM instruction set and build a processor out of it, and I can do it on an FPGA and be happy with it, but I can't go and commercially sell it. So maybe you will be able to sell it also. If you sell in 5-10 numbers, nobody is going to look at it. But suppose you are going to do it, mimic or build an equivalent ARM. You will call it your own name, you build something, but finally it's an ARM processor and goes into volume, you are going to end in trouble tomorrow or the day after. But here, it gives you the flexibility.
Number one, you can use the ISA as such. There are enough flavors of ISA you can use as such, or if the need demands, you can have a custom instruction set put in and have a custom flavor of the ISA, build it and use it for your application also. So that flexibility is there in this. So this essentially captures why we need such a program. So if you see any product today, right from your washing machine, your microwave oven, or your mobile phone, or a car, you will have microprocessors in various forms. So it's an inevitable thing, it's everywhere. It's crucial for public safety and critical communication also, because we take things lightly, but like Kama sir spoke in the morning, in some critical infrastructure, we are using all microprocessor, all systems are bought out. And if there is some bug or some Trojan sitting there and something happens, the system comes down and we won't be able to make head or tail of what is happening. So here, since from the ISA, you are starting from the ISA, then you are building your own RTL, you're doing the implementation in-house, you have full control of the design and you know what is in the design. The transparency is there in the design when you build it from scratch. And it's an essential component of India's ascent to technological supremacy also. We are not dependent on some other country for this because it's really essential. Similarly, as I mentioned, essential for space, defense sector, public utilities, commodities and communication. It's critical, strategic and is of national importance. And the country will have the control to change, proliferate, implement and guarantee availability. It's not that tomorrow some sanctions come in. You would have, all of you will be aware that US has put a restriction that classified the availability of GPUs, NVIDIA GPUs in A, B, C category. I believe we fall in the in-between category. A is you will get everything, B with some restrictions, and C you won't get. So we fall in the B category, but tomorrow if we fall in the C category, we won't get anything. So it's a real challenge, but I think we have made a good start, and there are a lot of companies now in India also working on it. So we are building things which will going forward enable us to reach definitely higher levels of indigenous technology. So again, the DIR-V, we have Shakti, and then I would say Shakti came first, and then Vega came after that. So Vega is the series of processors we have built in CDAC. We call it DIR-V Vega. So we have currently a flavor of RISC-V processors. We have 6 variants now, starting from a microcontroller class 3-stage pipeline to a 16-stage out-of-order multi-core processor. That's where we stand now. And work is going on, going forward to build higher order variants also, taking into account the other applications or the wider range of applications we need to support going forward. So as I mentioned, this is the current flavor of process we have. On the left-hand side, we have the lower-end microcontroller class, where we have a 32-bit single-stage, single-core 3-stage pipeline. Then we migrate to a 32-bit single-core 5-stage pipeline. Then we have a 64-bit in-order again 6-stage pipeline. Then we have the 64-bit out-of-order core 16-stage, which we have in single, dual, and quad flavors. So advantage for that matter is for Vega is that it uses an open source ISA, that's RISC-V. So the design is secure in the sense that it's fully transparent. It's done from scratch. We have the ISA from which we have built the RTL for that. And whatever physical design, we have a few silicon we have built using this, which I will come to in the coming slides. All that has been done internally. That is the RTL to GDS2 has been done internally, so we have full control of what we do. Of course, the fabrication, we have limited resource within India. So we have the SEL foundry where we have the 180 nanometer process, where we have done a tape out, and we have the silicon in our stall. The others we have done outside India, where the appropriate technology is available for fabrication. So this is the current roadmap we are having. The 1, 2, 3 we have done. That is, first we had a 32-bit microcontroller class variant, which we call Tejas 32, which is 100 megahertz design. And we have built around 8 development boards based on that, which are called Aries, which are now available both in vegaprocess.in website as well as Amazon and Robo.in. Few websites, the boards are available commercially. And the second silicon we are having is the Tejas 64, which is 64-bit single core 100 megahertz processor or SoC, which was designed and built in the SCL 180 nanometer fab. And the third one is the DIR-V 64, which is a 1 gigahertz dual core processor, which is again SoC, integrates a host of IP, which has been taped out in in TSMC 20 nanometer, and we are expecting the silicon back in the next couple of months, which is getting packaged. And the next one we are working on currently is the quad-core flavor of the processor, which will be a 2 gigahertz one, which again will be targeting the TSMC foundry. So this is the 32-bit one which you have done, and these are the specs of that. And I think again Venkat sir will differ, but see, we have built, I will just go forward and come back. We have built a few development boards based on it. So we have made it Arduino compatible. So I had Venkat sir was saying that we should not say, we should say it's Arduino compatible. But initially what we found was that we have a board, we go to any college or any student, most of them would have used Arduino. So they will be comfortable with that. And here we have an IDE again, but somebody's kind of used to it. And when we say that use that IDE, they are not comfortable. They will say, it's Arduino, I'm happy, I'm using, why should I use your board? So what we did was, whether you like it or not, we did it. We have an Arduino port for this. So a user who is familiar with Arduino, he can straight away plug that V3 board into his, we have made even the connectors, everything 100% compatible. So your Arduino shields you get from the market, you can straight away plug in. There are two schools of thought. One is we should not do that, but initially we faced a lot of resistance because people have something, they're comfortable with something, they are hearing something for the first time, Vega, what is Vega, what is Aries, nobody knows, what is CDAC, nobody knows. So, the student community may not know. So we go to colleges also, they have that initial apprehension, whether this will work, do we need to use that? We are already having something which is proven, right? So to make life easy for who is going to use it, we made it Arduino compatible so that all the Arduino shields work, and you get a lot of programs, firmware for various sensors which you want to plug in the Arduino, it's available, all that works seamlessly. So, so these are currently the 8 development boards we have done based on Tejas 32, where IDs, all of them are Arduino compatible, and we have our own IDE, but again adoption is more for Arduino because people are comfortable with Arduino, right? So starting from the V3, which is kind of compatible with the Arduino board, others have other features. I have details in the coming slides. So I'll just go back. The second silicon which we have done, where the silicon we have in hand, and we have a test board, and development board is work in progress. Maybe in the next couple of months we'll have the development board out, is the Tejas 64, which is a 64-bit in-order processor based on which we have built the SoC. So in both these, the Tejas 32 as well as 64, the SoC has got, if you see here, it has got other IPs as well, UART, SPI, timer, PWM, I2C, GPIO. So these are all slow-speed peripherals, but all have been built in-house. What I want to emphasize is the design is 100% known, design is 100% internally done. Even the physical design, everything is done internally. Only thing is fabrication and packaging, you have to go out. So this was done in Siltara 130 nanometer, and this one was done at SCL. There again, the design end-to-end is done internally. Here we have a 64-bit processor, then we have all these low-speed interface, plus we have a SDRAM controller, we have an Ethernet controller. All these controllers, everything is designed in-house. The fabrication is done in SCL. The packaging we did through a private party outside because we did a 400-pin globe-top BGA package. So that SCL has some limitations in BGA packaging. So we went out and did it in another company in India itself. So it's again a 80 megahertz CPU targeted for embedded and IoT applications. And this is the development platform I spoke of, which mimics Arduino. so that the Arduino boards can be replaced with this. Then we have other flavors of the boards also. One is called Alpha, where you have onboard interfaces like SD card reader, Ethernet controller, then a standalone CAN controller. As I mentioned, see, when we have one, initially we had V3 only. So when we look at some users, it can be academia or industry itself, they will ask for more and more interfaces. So we don't have the luxury of building silicon where we have A variant, B variant, C variant. It's not possible. Practically, I mean, theoretically you can do that. There's no challenge in that, but practically you can't do that. Every year you can't have variants coming out just like that. I mean, we don't have that kind of funding. So what the viable way out was have boards which support these features. So we brought out many flavor of boards which support different features, so that the industry can use the silicon, test it out, and there are scenarios where there are at least few companies whom we are now active discussion with, who need not the AS32 but something plus and something minus. So basically they are now confident that this thing works. So now we are in the stage where we can license the IPs out and they can build the silicon with our support. That's the kind of model we are working on. Similarly, another platform we have built is an IoT platform where we have on the board we have digital proximity sensor, ambient light and gesture sensor, an accelerometer, gyroscope, gas sensor, humidity sensor. Then we have a Bluetooth Wi-Fi module also where you can connect to the web. So this again was done because there were requirements where from the industry as well as academia, they want to build products or projects based on IoT. So this was built based on that. So as I mentioned, using the Vega processor, we can build multiple applications. You can use it for Internet of Things, Internet of Everything. Then we can use it for smart meters. We can build reference boards. We can have point of sale systems. So there's no limit in what we can build, right? We need to configure and build the appropriate SoC for that. So what are the key benefits when we look at indigenous processor? For that matter, not even Vega, for Shakti or any of the indigenous processor startup companies are there, like Incore who are building it. So what is it? So India will own the IP for all these processors, fully indigenous. We have the total implementation. You can interact with academia, you can have a direct interaction with academia, you can support them as well as industry, and it is fully indigenous. There's no third party coming in. Then it's we are fully self-reliant. We are not depending on anybody else for building the cores. So the aim is to pave the way to have India design and manufactured electronics, chips and hardware leading to success in Make in India initiative, which I believe is happening now. You saw the silicon from CDAC Vega. Similarly, we have Shakti Silicon. We have now silicon from MindGrow. And we have our partners who are here in this room. I am not going to name them. I don't want to do that. From my side, I don't want to differentiate, but there are partners in our room who are on the way to build silicon, and maybe in a couple of years' time, we will have real silicon coming out. Can be from Shakti Vega or some variant, but I am sure that I'm confident that in a 2 years' time, worst case in 2027, we will be seeing products which are going to scale based on indigenous RISC-V based processors. And another thing, like earlier speaker was mentioning, it's not just the processor. We need to have an ecosystem. We need to have reference boards. We need to have an SDK. We need to have the software ecosystem also for that. So we have also put in considerable effort into that. So you can visit the Vega processors.in website. So where we have all these boards listed, we have a Vega SDK. We have a YouTube channel where we have demonstrated or captured videos using connecting multiple sensors, multitude of sensors and actuators, different applications which you can build using this. So all this ecosystem needs to be built. It doesn't happen in a day, it takes time, but we are on track for doing that. Because with that only you will have adoption. Otherwise, the processor or silicon you can always have. But unless and until you have all these collaterals, nobody will be able to adopt this. So these are some of the Vega-based products which not us, but some of the partners or our customers have built. CG Core has built an Advik-based Vega embedded kit, which we hope that in the next coming year or within this year, that is 2025, we'll see this in the market where they will push into academic institutions. Similarly, there is a group in CDAC who build traffic controllers. So what they have done is they were using a COTS-based design, an ARM-based microcontroller for their application. So now they have migrated that board to a Vega-based silicon now. Similarly, the AR lab and IAC have built a drone controller using a Vega-based silicon. So that again, we are working with the professor so that this can be taken forward to the next level. Similarly, one of the groups in again CDAC have built an indigenous ultrasonic liquid level sensor. So most of these cases, what has happened is they were using quartz-based design, they have migrated to a RISC-V-based alternative Vega. So there is not no dearth of opportunity. There are umpteen products you can migrate, but again, it's not an easy path. There is a lot of effort and I would say stress involved in this. It's not an easy path. Getting people to adopt an indigenous design is never easy because we have been using all these imported stuff for so long. So always the question, the first question, you talk to anybody, documentation, that's another thing which is difficult. We struggle with that also. It's not a small thing, getting everything in place because big companies, they have built a repository of things over many years. It's not just something they have built overnight. There are companies who have built this repository of tools, infra, documentation, simulators, everything. It has taken them maybe 25, 30 years to, they have evolved and they have reached a stage. So when we start off, we don't have everything in one day, right? So I would say we're all doing baby steps, but I believe that we're on the right track. So at least few people we have been fortunate to convince, and they have convinced. We're happy to work with few people who adopted Vega. Similarly, Shakti also people are adopting. So at least few of them are shown the courage. I would say the courage really, because to adopt a new architecture, a new processor, which has not gone into millions or billions, of course, but through those partners, we believe that we will be able to do it in the coming year. Similarly, a team in CDAC, they have a power electronics group, they build smart meters, they built a three-phase smart energy meter using Vega. So that again, now we are seeing how we can take it to volume production. So always the challenge is from the perspective, from a designer or from our perspective is you can have a lot of prototypes, but taking it to production, going in for mass volume is a different ball game. A lot of challenges are involved, and it's not an easy thing. So from a different perspective, you can always question, like what the hell you have done, what is the big deal, you have done only this much. I mean, we hear all these things. You will say that only you have only this thing. That is already available in the market. But please understand that that has been built from scratch, and the know-how is fully known. We know end-to-end what has been built, and the capability is there to adapt and change it so that tomorrow you want a change. We need not go and stand in front of somebody and say, sir, please make that change for me. I don't have control of the design. It's not like that. We have full control of the design. That's the advantage. So I would say, a hard path or a difficult path. A lot of thorns there, but I think all of us will together circumvent or go over that, right? It's not an easy journey that we are doing, whatever. I mean, not from the Vega perspective, from any RISC-V startup in India, I would say. I don't want to comment on the outside world, but in India, it's not an easy stuff to get things done. So as I mentioned, we are in our, I would say in a small way, we are trying to proliferate and build an ecosystem which will enable users to adopt the RISC-V processors. So that's why we have a set of hardware development boards. We have the SDKs and also the reference design. It can be on in terms of silicon, or in another case it can be on FPGA also. So somebody is interested, we offer them the FPGA solution so that they can use the real hardware and have or build confidence that this thing genuinely works. So how can we contribute in the semiconductor vision, India semiconductor vision, CDAC? So as you know, CDAC is doing pioneering research in advanced computing technologies over years, And now we are on into developing indigenous process as well as computing solutions. And we have a active engagement with multiple startups as well as industry, so that it's not possible for CDAC or for that matter any company by themselves to do everything. So we bring in the cores and IP and the expertise we have built over the years in FPGA based design as well as ASIC we have developed over the years. We build that in, and we are now collaborating with at least a few startups and helping them to build silicon which can go into volume and which can go into products. That's the approach we are taking. And similarly, I strongly feel that academia also has to be there. So we are also actively doing that. Every year we conduct, not every year, every month. Now we typically conduct at least one workshop. We make sure that we conduct one workshop in academic institution right across the country. We have done it up from Jammu and Kashmir down south. We have done it. Chennai we have done it. We have gone to Gujarat, Rajasthan, every place, Delhi, Calcutta. We have covered almost all across the country we go, and so that I would say it's more for people to understand what is RISC-V, the kind of work which happens in this domain, and they make the academia or the students familiar at least with the work which is happening in the country, so that they can all contribute to the work going forward. So that is actively being done. And we are now also supporting academia. Earlier, our friend Sharat spoke of the C2S scheme. So C2S scheme, government is funding actively a lot of academic institutions where they work on building real silicon end-to-end. They provide the tools, the infrastructure, as well as the tape out is taken care of. So we are working with academia also, so that we can support him by providing the core and IP, and support them in building the silicon. So that finally it's not just industry, academia also has to play a role. Then only we will have a continuous chain of people who are interested in this area, and will have real innovation happening. So we have, I would say, umpteen challenges. Opportunities are there, but umpteen challenges are also there. So strength is, of course, it helps build self-reliance, foreign dependency. We need not have an DIR-V program. I believe acts as a gel kind of stuff between academia, industry, so that, and government institutions like CDAC, so that we can all come in and build silicon. And there is, I believe that there's enough or more talent in the country. Only thing, we need to channelize them and make them interested and make them work in this area. So we have weaknesses also, which maybe in the coming years we will be able to circumvent or overcome. We are, for fabrication today, for packaging today, we need to do a flip chip BGA package. Typically we need to go outside. I am not sure whether we have capable teams of doing flip chip packaging in India. Wire bond we have done. The Tejas 64 was wire bond. It was a 400 pin wire bond BGA, which we could do here. But you go for advanced packaging, I am not sure we have today. Maybe in a year's time we will have going forward. So that is again a grey area. Fabrication, of course, maybe in the coming maybe 3-4 years we will have the foundry coming up, and we will have that happening. Otherwise, you want to go for advanced nodes, we have a challenge. We have to go outside. There's no way out. And again, there are other things where we have challenges which I have not listed there. There are end challenges. The tools which we are using, we are dependent on limited to typically three people. I don't want to name them. 3 people or companies are the ones who supply the tools. So that is another area where I'm not sure whether work is happening in India in that area, where we build tools. We use a lot of tools to convert this RTL to silicon. So all those tools right now are imported or come from outside, typically. So because another challenge is we can have some open source flavors also, but moment we talk to a foundry, finally we want to do the design sign-off and all, they will only use certain standard tools. So that challenge is always there. And then IP. That's another thing which I find, which when we try to build, we find limiting in the sense physical IP. Or of course we will say that we can have digital controllers we can have, but when you talk about physical IP, like we have a USB controller design in-house, but we don't have a physical PHY we don't have. Similarly, you look at Ethernet, we have a controller, but we don't have the PHY. Similarly, you look at AS32. So one question being asked to us is, why don't you integrate in ADC? Why did you not do that? Now the point is, ADC, if we want to integrate, we don't have any Indian company. Okay, today I know a couple of companies are there, but 4 or 5 years back, there were not many companies who have proven analog digital converters or digital analog converters, or for that matter, a PLL, which is proven on silicon, which we can pick up and use. There are very few companies. So mixed signal design is another area where, if you ask me, it's a big challenge. We don't have many companies. There are niche companies, few, which I know of, who are working or doing good, but that you can count on the fingers the number of companies who are doing work in that area. But that's another area where we have a huge gap. There are certain IPs which, for example, a Bluetooth IP, which we need for some of the other projects. If you ask me, in the world, there is only one company we know of who have got a proven IP, Bluetooth, the stack, the entire stack, the controller plus the PHY, plus the radio, everything. There's only one company who has it. And we had some initial discussion with them, because we will finally need to use that, because we don't have any other choice. So some IPs or some IP like mixed signal IPs, we don't have much work happening in India. So that is another area where, I just did not list all those. So those are things which, there are a lot of opportunities. Those are niche areas which we need to work on. If we want to be truly indigenous, we need to have that also. Because processor only one part of the story, fab coming in is another part of the story, but there are a lot of other bits and pieces. Of course, India as a country can't do maybe 100%, but these are things which we can do, because we have strong engineers coming out. So there should be, some policy decision or something, so that we invest more in that area and bring IP, not just digital IP, mixed signal, physical IP or PHY IPs, ADC, DACs, PLLs and power regulators. There are a whole range of things which you need. You want to build an SoC, you want to make it work from a single power supply, then you will say you need converters inside or regulators inside. So what do? You have to again go out and get it. We don't have that in the country today. There are, but again, niche, only a couple of companies. So the opportunities are immense, and the good thing is government support is coming in a big way. We have the DIR-V program, then we have the DLI scheme, through which a lot of startups and industry is getting supported, wherein they are going to build real silicon. That's a really good initiative. Then we have the C2S program, which I have been running, again all by our parent ministry over past so many years, which is really good, because it enables somebody who's really interested to learn these things, build a silicon, see it on its table, build a board and test it. So government is supporting all these things. And then we have the PLA scheme, and as part of the DLA scheme, we have the tools, IPs, everything is being provided by the government, supporting them at a subsidy cost. So I would say that like our Rajiv Chandrasekhar was saying, it's the right time to be. At least a lot of support is there from the government, as well as the environment is proper, everything is proper. Only thing is we have to work towards that, and it's not an easy job. It's really hard. No offense meant, but it's not like software where I key in something today, it doesn't run, I change and run tomorrow. It's not that difficult. Even though you may have a small board, but getting it up and running, it's going to be a challenge. You need to make your hands dirty, spend a lot of time and effort to get things right. It's not an easy thing, because I've been working on this. I know the challenges involved, and why I am saying this, because you are a student community, so I can tell that openly. Some other forum I won't say that, because there are people who don't understand these things. People think that's just like that. Like building hardware is like going to a market and buying 1 kilo of Vendaka and 1 kilo carrot or beans. It's that easy, people think. It's not that. Even you want to build a PCB of your own, let us say you have a reference design available, you build a board, put some firmware on that, make it up and running, considerable effort is required. Forget about the semiconductor stuff and all. You have all these things available, somebody is giving you a reference design, you have the Gerber, fabricate it, assemble it, up and running, it is a pain. It may not work. So it's really difficult, and I'm sorry to say that, but what I, through my experience, I found that many people don't understand these things. So that is a bit of a pull down for us when you build something and people don't understand the challenges we go through. But that's a different story. Anyway, so threats are also always there. So India's competition from established global semiconductor giants is always there. So tomorrow you are going to build something. I know you want to build something, and the established company sees that it's a threat. You may not even have started. You will have these people approach, not you, but the higher ups who make the decisions, and tell them that, boss, I will give everything to you on a platter. Why are you bothering to go and build all these things? We will collaborate. We will offer you everything. Why do you want to build? We will give you everything. So that it makes your life easy. But the fact is, you do that, again you are at the starting point only. You are again dependent on them. So there are enough threats and challenges, and India is a huge market. So people, it's not easy. It's not an easy thing going forward. So I would like to conclude. I think I took a lot of your time. So I would very, very authentically, and I would I mean, it comes from my heart. India has made significant progress in developing indigenous process technology. There's no doubt about that. I'm not seeing from CDAC perspective. We have Shakti, we have Incor, we have Mangrove. Many companies have spawned out and working. There are other companies also. So we have made significant progress, and we are going to make progress. There's no doubt about that. And the DIR-V program is leveraging the open source ISA and has driven innovation chip design and has enabled to foster collaboration with industry leaders also. And in whatever small way, the Vega processor ecosystem, we intend to support a wide range of applications and the growth of indigenous SOCs and product development. That's, I would say, what we can do in a small way. I would say in a small way because we have limitations. That's why I'm saying a small way. CDAC can't do everything. So in a small way, we are also contributing, and we hope that going forward, as I mentioned, maybe in the next DIR-V similar meeting or the symposium after that, maybe the next year one, we will have at least a company coming on stage and showing that this is our real product we have made, and this is selling in not 1 number, 2 number, 10 number, maybe a volume is maybe 500,000 per annum, or let us say 1/10 of a million per annum. I truly believe that is going to happen in at least a couple of years time frame. Thank you. Thanks for your patient listening.
Thanks for the lively discussion. We come to the end of the session for day one. Thank you all for staying back till the last session. We will come back again tomorrow by 9 a.m. The session will start for day two. Thank you all.